and wish you the best of success. And wish of the best of success in all the activity you carry out. I hope you will enjoy the following days of debate and networking. Thank you for your participation. Thank you, Mirai, for this moment. Thank you all people that participate in this interesting conference and School of Computational Intelligence. Thank you.
Thank you very much, Jorge. In the following, we are going to ask to the president of the steering committee, Dr. Fernando Buarque, to welcome us.
So, good morning to you all. I hope you are listening to me well. The official language of IEEE LA-CCI is English, of course, but please allow me to greet our hosts and some delegations in their own language. Entonces, buenos días a todos que hablan castellano. Los saludo a todos desde Recife, en noreste de Brasil. Gracias al decano de la Facultad de Ingeniería de Ciencias de la Universidad de la Frontera, Temuco, profesor Jorge Farías, por recibirnos. En su nombre, saludo a todas las autoridades participantes, queridos colegas profesores, estudiantes y visitantes. Un gran agradecimiento especial a la profesora Milarey Kurbileman por el arduo trabajo de organizar esta conferencia con su gran equipo. No es nada fácil, todos sabemos de esto. Es una pena no estar contigo todos en Temuco, Chile, en la hermosa región de Araucania, en Chile. Muito bom dia aos lusófonos. Aparentemente, temos a maior delegação do Congresso. Obrigado por terem submetido seus trabalhos. É um prazer recebê-los a todos. Bienvenue aux francophones. Willkommen bei den Deutschen Sprechern. Benvenuti agli oratori italiani. Willkommen agli afrikanischen Sprechern. Ninjane. I'm terribly sorry because Danish, Indian, and Pakistani authors will be warmly greeted in English. Your language is out of my league. Well, I don't want to deliver a long speech, but it's important to note that since 2014, LA-CCI has been held in different Latin American countries. That's the 7th edition. It should be the 8th, but last year we could not because we were at the peak of the pandemic. But we visited 7 countries now. So the first LA-CCI was in Bariloche, 2014, then in Brazil, Curitiba, 2015, Cartagena de Indias in Colombia, 2016, Arequipa, Peru, 2017, Guadalajara, Mexico, 2018, Guayaquil, Ecuador, 2019, and then we had the pandemic. But now we are here gathering in Temuco, and I am very sure that we will have a great conference. In all editions of LA-CCI, the organizers put together great conferences with a collegial and pleasant environment. Thus, thematic sessions, schools, competition, and discussion panels are especially tailored for attracting and pleasing greater audiences. It is important to notice that in Latin America, we should have conferences like that because we have great potential as scientists, as countries, but somehow we are underrepresented in the scientific world. So this is an international conference organized by Latin people, and therefore the idea is to really portray what we have and to welcome people from other nations, from other parts of the world. This year, the organizers had an extra effort of because of the pandemic. So thanks a lot again for the team that organized this edition. Was not easy, but the local organizers put together a brilliant conference. You have seen the virtual lounge. So it was a brilliant work. So 17 countries are represented here, closer 100 submissions. So this is nice for a period, a challenging period like that. This is really perfect. And this year, we, the former steering committee of the conference, decided to merge into IEEE, the Computational Intelligence Society. So somehow that was a natural decision, because since 2016, all the events were officially sponsored by IEEE. And then we recently decided to merge, and now we are an official conference of IEEE under the Computational Intelligence Society. So this is great news. I think we will have more, how can I say, coherence along time. There will be a greater degree of standardization and perhaps a better spread within the continent. But my final words are regarding these challenging moments we live currently. So I hope that this gathering of scholars, government officials, students, which are the future of academia, by the way, we have to treat you very well, the students, the funding agencies that are listening to us right now. It's very important that we keep the flame of science burning, because science was the reason we came out of the cave, in using Plato's allegory of the cave. But currently, science is being challenged. It is unbelievable that in the 21st century, we still have people denying science and all the stuff you probably listen every day. So we have an extra responsibility to work diligently on this area, which is the center of the intelligence age, the fourth industrial revolution. I prefer to call it the fourth human revolution. We have lots of problems. We have this new Cold War, which is very worrying. We do have risks of new pandemics. We have threats from bad use of AI. So there are lots of challenges. And the only way, to my opinion, that we can face those is if we brace together, use education, science, and technology for the flourishing of societies. Our Congress is a small brick in this nice, not wall, bridge from the current state to a brighter future. So I will finish my brief words here saying that I'm very optimistic that if we use AI in the right manner, it could be the solution for many of the problems I referred 1 minute ago. And I take the opportunity to invite you all for a physical conference next year in November in the beautiful city of Montevideo, Uruguay, where we will have the 8th LA-CCI. So I wish you all a great conference. I thank again the host institution, the brilliant team of Miller Ray. I know you will never want to organize a conference in your life, but this happens with everybody, okay? You have done a great deed. Thank you very much. I wish you a great conference. Thanks.
Thank you very much, Fernando, and thank you very much for your energy, the energy you put to this organization. Thank you very much. We will have a meeting, in fact. Well, Going on with the description of our conference, I want to inform you that these were the papers sent to us in total 79 papers from those countries, 17 countries, where we cut the acceptation to 56 points in the evaluation of the reviewers. So the papers were very well evaluated. We had a 50, but a 50 points threshold, but there were too many papers. We had to increase a little bit. Thank you very much to the authors and all the people that sent their papers to the conference. The program is divided in morning and afternoon. This is the morning of every day. As you know, the Latin American conference is together with the summer school. And you will have the conference exclusively Tuesday to Thursday, but Thursday in the morning will be for both together, EVIC and LA-CCI. Friday is EVIC. Everyone that was registered to the conference is available to go to the summer school also, everyone, okay? In the morning, we have the key speaker talks organized here in these sessions, where you will be able to interact with the speakers. This is very interesting if you have questions. And we will have also 2 outreach sessions that are in parallel from the conference, and that are where many people of the community are invited. So I recommend you to invite people of your environment to this conference because they are going to be free and they are going to be transmitted by YouTube. We will send the information, and the information will be available in the platform of LA-CCI. We have 2 interesting conferences of Pablo Seger that is going to talk about the technological entrepreneurship in Chile. Pablo is the founder of a company, an artificial intelligence company in Chile. So he knows very well what are the challenges in this area. And the second day, we will have considerations on ethics and artificial intelligence applications. A very interesting talk where we are going to touch these conflicts sometimes between artificial intelligence and human rights. So these are the plenaries. You have then them in the platform. This is the organization of the morning. All these talks will be in the plenary room. We have only one room by activity. So all these will be in the plenary room. In the afternoon, we have the technical sessions from Tuesday to Thursday, and then Thursday it will be in parallel the tutorials of the summer school, okay? And Friday, of course, it will be only the tutorials. So the sessions, you should go to the platform to look them. Here you can go, you can make click to go to the virtual rooms. You received a login and a password to enter here, and entering here. Here is the contact. Please look at that if you haven't. Okay, Contactos of Telisa send you the password and the login, and you will be prompted to this environment when you have here the plenary rooms, and the other rooms. And you can, I will switch to the, where is my, excuse me. here. And if you link to the schedule, you will have the schedule by day, Tuesday, Wednesday, Thursday, etc. And you can click here to go to any conference you are interested in. For example, in the this is the plenary room. Here are the technical sessions. You can have details of which are the sessions here that will be happening. We are not going to delay the session. If someone does not present, the space will remain black. So the schedule is not modified. So you can plan your participation in all the sessions. Here are the sessions, and well, Thursday it is also the sessions and the tutorials. Okay, so here in this platform you will have very organized all the planification of the event. Well, to finish this, just to say that you're very welcome to our conference and the summer school. I hope it will be very enriching, and we will have a lot of conversation about these so important topics for the, as Fernando said, the evolution of humanity. Where are we going with all that? It will depend in some way of the work of all of us. So very welcome to everyone. Thank you very much to the key speakers that are enriching and making the level of this conference is very high. Thank you very much to all of you. Thank you. So this is the end of this opening session. It's 9 o'clock. We are going to start with the first conference, but I don't know if someone wants to say something very short. No, Doris? Okay, so we are going to start with our, here is Carlos Coelho, who had to wake up very, very early. So I don't know if Maria Cristina Riff is here. Wait a minute, I'm not sure here. Maria Cristina Riff, who is the chair of this session. No, she's not. Carlos, I will present you so, okay? Well, in the first place, I want to thank you very much for accepting to be here once again, because last year you also accepted to be our key speaker. So thank you very much for being here. And I present Carlos Coelho, that he received the PhD degree in computer science from Tulane University, New Orleans. He is a professor with the Department of Computer Science in the Sinvestav, it's okay? Sinvestav, Mexico City. He has authors and co-authors over than 500 technical papers and book chapters. His publications currently report over than 49,000 citations in Google Scholar, and with an H index of 86. His current research interests include evolutionary multi-objective optimization and constraint handling techniques for evolutionary algorithms. Dr. Coelho has been the recipient of the 2027 National Research Award from the Mexican Academy of Science in the area of exact science, and the 2013 IEEE Kiyo Tomiyasu Award in Engineering Science, and in 2012 National Medal of Science and Arts in the area of physical, mathematics, and natural science. So once again, welcome, Carlos. The conference is Where is the Research Evolutionary Multi-Objective Optimization heading to?
So let me see. Can you see my screen there?
Yes.
Yes.
It's very okay. Thank you very much. Carlos will have approximately 1 hour to make this conference, in which, Carlos, please let a time for questions, okay? You have 40-50 minutes for your conference. Thank you very much again.
Thank you. Thanks for the invitation. So this talk is focused on trying to show a small sample of the large amount of research that has been conducted in a field that is now called evolutionary multi-objective optimization. But this is not to say that there is nothing left to be done in this field. It's the opposite. Try to motivate research ideas and things that can still be done. It's probably not as easy as it was 25 years ago to get into this field, but it's still possible. It's just you have to look carefully, as opposed to 25 years ago in which there were so many topics available. So this is the idea of this talk. I will start with a very short introduction to multi-objective optimization in case you are not familiar with the topic. Basically, in this area, we deal with problems that have 2 or more objectives, but the key element here is that these objectives are at least partially conflicting. That means that improving one implies worsening at least another one. So this is an example of a bridge. I want to optimize the design of a bridge, and some obvious objectives will be the cost and the structural safety of the structure. So if I want the structure to be safer, normally I have to increase the amount of material, and this will increase the cost. So cost and safety are contradicting to each other. Because of the conflict, these problems are really ill-defined in mathematical terms. This means that there is no simple solution to them. Actually, there is no single solution. So this is the definition. I have k objectives where k is greater or equal than 2. And I may have also inequality and equality constraints. And what I want is to find a vector of decision variables that satisfies all of this. The first issue in multi-objective optimization is the notion of optimality, which is not the same or is not as intuitive as in global optimization. Actually, there is more than one, but the most popular one was originally proposed by Francis Isidro Edgeworth. He was a professor at Oxford University, and in his book entitled Mathematical Psychics, published in 1881, he describes a notion of finding good compromises or trade-offs, rather than finding a single solution as we do in global optimization. However, it was Vilfredo Pareto, an Italian economist, who in 1896 publishes his book Cours d'Economie, in which he generalizes this concept, although he was not aware of Edgeworth's work. So he derived the concept on his own. This notion that he originally called ophelimity has been renamed over the years to Edgeworth-Pareto optimum, but at some point in history, many people started to remove the last name of Edgeworth, and is now known only as Pareto optimality or Pareto optimum. It's very intuitive, this definition, if we assume that all the objectives are being minimized, and this is a reasonable assumption because it's always possible to transform a maximization into a minimization, then the definition is this. We say that a vector of decision variables, which is feasible, that means satisfies all the constraints of the problem, is Pareto optimal if these conditions hold. There is no other solution that is feasible that satisfies that is less equal in every objective and strictly less for at least one of them. So it's a very, very simple definition. Basically, what the definition says is that for a solution to be Pareto optimal, this implies that no other solution that is not possible to improve any solution without worsening any other in the set of solutions that we have. Because of the conflicting nature of the objectives, the definition will give us not one, but a set of solutions. This is called the Pareto optimal set in decision variable space. And the image of this set, that is the objective function values that correspond to the Pareto optimal set, is called the Pareto front. Solutions that correspond to the contents of the Pareto optimal set are said to be non-dominated. So we normally talk about non-dominated solutions, which strictly speaking is not correct, but it's a very common term. So obviously, before we use evolutionary algorithms, people were already solving multi-objective optimization problems using mathematical programming techniques. There are a number of techniques and families of algorithms. And these algorithms are actually very fast, very efficient, but they do have some limitations. The main ones are that they normally generate the elements of the Pareto optimal set one at a time. Also, most of them are very sensitive to the shape and the continuity of the Pareto front. And this prevents the use of these techniques in some problems. The idea of using techniques based on the emulation of the mechanism of natural selection to solve problems is a very old one, although it was until the 1960s when the first algorithms based on this notion were developed. So we do have genetic algorithms developed by John Holland in the 1960s, evolutionary strategies developed by Ingo Reichenberg and Hans-Paul Schwefel in also 1960s, and evolutionary programming developed by Lawrence Vogel also in the 1960s in the US. So these approaches are now called collectively evolutionary algorithms, and they are particularly suitable to solve multi-objective optimization problems because they offer an interesting advantage, the fact that they operate on a set of solutions, what we call a population. So this allows us to find several elements of the Pareto optimal set in a single run of the algorithm. Of course, this requires some manipulation to do it. So this is better than using a mathematical programming technique in the sense that we don't need to execute several times the algorithm to generate one element at a time. We can generate several in a single execution. Additionally, because of their nature, they are black box optimization techniques, evolutionary algorithms are less susceptible to the shape or continuity of the Pareto front, and they don't require additional information about the problem, such as the derivatives of the objectives, for example. So to understand the growth of the field in one topic, which is algorithms, is the first topic I will mention, I will briefly show you a taxonomy of multi-objective evolutionary algorithms to give you an idea of how the field has developed since its origins in 1985 with David Schaefer, who proposed the first multi-objective evolutionary algorithm. It was called VEGA, the Vector Evaluated Genetic Algorithm, which is a very naive approach. And there were several others in the old days. This goes from 1985 up to 1992, 1993. The so-called non-elitist, non-Pareto based. That means they don't use elitism and they don't adopt Pareto optimality in their selection mechanism. So we have, for example, lexicographic ordering, which is very simple. Linear aggregating functions, they are still popular today. This is basically adding up all the objectives into a single scalar value. We have the epsilon constraint method, which is a very interesting one, but has some limitations. And the so-called target vector approaches, these are non-linear aggregating functions, which, unlike linear aggregating functions, are more powerful in the sense that they can generate non-convex portions of the Pareto front, something that linear aggregating functions normally cannot do. However, target vector approaches, as the name indicates, they require target values. And these target values are not trivial to find. Then in the mid-90s, there were several algorithms that were developed based on a discussion from David Goldberg in his famous book on genetic algorithms. David Goldberg analyzes what had been done on multi-objective optimization back in the year 1989 when he published his book, Genetic Algorithms. And basically all he found was Vega. He said Vega is the only thing that has been done. And he gives an informal discussion saying, if I had to solve a multi-objective optimization problem, this is the way in which I would do it. And this description is what we call Pareto ranking. And people started to work with this idea. And then a few algorithms were developed using variations of Goldberg's idea. So we have, for example, MOGA, introduced in 1993 by Carlos Fonseca and Peter Fleming at the University of Sheffield, which uses a more efficient way, a more efficient mechanism for doing Pareto ranking. Then we have the non-dominated sorting genetic algorithm introduced by Kalya Moidev in 1994. This is the algorithm that follows more closely the description of Goldberg in his book. And then the MPGA, the niche Pareto genetic algorithm, introduced by Jeffrey Horn in 1994. This is actually a very clever algorithm in which instead of using the whole population for doing the ranking or the non-dominated sorting, they use only a sample of the population. Then we have what I call the contemporary approaches. These are already elitist. Elitism in this field means to have a mechanism to retain the non-dominated solutions that are generated by the algorithm so that they are not destroyed by crossover and mutation. And these, of course, they are all Pareto-based in the sense that they incorporate Pareto optimality in their selection mechanisms. So we have, for example, the strength Pareto evolutionary algorithm introduced by Eckhard Sitzler back in 1999. We have NSGA2 proposed by Kalya Moidev in the year 2002, very popular algorithm, still today is popular. There was SPEA2 introduced in 2001, the Pareto archive evolution strategy proposed by Joshua Knowles in the year 2000, and many, many other algorithms, including the microgenetic algorithm for multi-objective optimization and the microgenetic algorithm 2 that we introduced in my research group. The microgenetic algorithm was proposed in 2001 and the other one in 2003. Most of these algorithms have been already forgotten, but they were used at some point many years ago. Then finally, I have what I call the recent approaches, although they are not that recent, but some of them, like MOIA-D, is really a family of algorithms rather than a single approach. So the original algorithm was introduced in the year 2007, but today we have a wide variety of variants of this algorithm that are still being published today. So that's what I say, this is really a family of algorithms. MOIA-D uses a notion that we call decomposition. I will get into this in another slide. Then we have another family, which is very interesting, what we call the indicator-based approaches. These are algorithms in which, in the original idea, instead of using Pareto optimality, we will use a performance indicator to select solutions. It turns out there is only one that fulfills the mathematical properties to do this. It's called the hyperbolic. But I will get to this also in another slide. And then finally, we have NSGA3, which was published, this algorithm was published in 2014 in the Transactions on Evolution Computation, and is intended for what we call many objective optimization, that is problems having more than 3 objectives. It's meant to complement NSGA2. It uses reference vectors, but in its design is similar to decomposition, is similar to MOIA-D. So after 36 years of existence and with so much work done, this is a field that may seem intimidating to people. If you want to do research in this field and you are not familiar with it, this may be frightening because you will find thousands of papers and perhaps no direction where to go. So the idea of this talk is to give you a few ideas, a few hints. So first, let me explain very briefly what we have achieved in terms of designing algorithms, because this is the area in which I have worked mainly the last 25 years. So there are three types of multi-objective evolutionary algorithms that are still being used today. The so-called Pareto-based, the decomposition-based, and the indicator-based multi-objective evolutionary algorithms. I will get to them very quickly. So let's start with Pareto-based. These are the traditional multi-objective evolutionary algorithms in which the selection mechanism is based on Pareto optimality. Most of them adopt something that we call non-dominated sorting or Pareto ranking. This is basically a ranking procedure that allows me to identify the solutions that are non-dominated in the population and to give them a higher fitness value so that they are favored in the selection process. Most of these algorithms also use something that we call a density estimator. The density estimator is a very important mechanism because it prevents the algorithm from converging to a single solution. It allows the generation of several solutions in a single run, something that we want because I mentioned before, this is one of the advantages of the multi-objective evolutionary algorithm. However, this is not done automatically. We need to provide a mechanism to ensure that this happens. Over the years, people have used a wide variety of density estimators, including crowding, fitness sharing, entropy, the adaptive grids, parallel coordinates, and so on. Some of them are not scalable. That means they cannot be used with more than two objectives. That's the case of the adaptive grid. Others are scalable, like fitness sharing. And there are others that have been developed only for particular cases, for particular problems. What is the main limitation of these algorithms? The main limitation is scalability in objective function space. What happens is that as we increase the number of objectives, unless we increase a lot the population size, the number of non-dominant solutions will grow very quickly. And therefore, the selection mechanism will become useless because you will be selecting at random because everybody will be non-dominant. There are alternatives to solve this problem. One of them is to change the density estimator, but still, this is not the solution that most people like. They prefer to design new algorithms. Second family is very interesting. It's called decomposition-based. And in this case, the idea is to transform a multi-objective optimization problem into several single objective optimization problems that are solved simultaneously using something we call neighborhood search. This is actually a very intriguing idea that comes from operations research. For this transformation to happen, you need something that we call a scalarizing function. It turns out that a couple of years ago, somebody discovered that the main weakness of these algorithms is precisely the scalarizing function. Why? Because in decomposition-based algorithms, scalability is not a main issue. You can increase the number of objectives and everything will work except that you will need more weights, which means that you are likely to need a larger population size. However, in this case, the increase in the population size is linear. It's not exponential and in the case of Pareto-based. So it's affordable. Normally it's possible to do it. But the issue is really that these algorithms are sensitive to the scalarizing function that is used. In fact, it was found that the scalarizing functions in current use, they fit to a simplex. That means that any Pareto front that doesn't fit with that geometrical shape is not appropriate for these algorithms. And there are, of course, people working on this right now. But if you do something as simple as inverting the Pareto fronts of traditional benchmark, like the DTL set test problems, decomposition-based algorithms no longer work. The last group is, for me, the most interesting one, the so-called indicator-based multi-objective evolutionary algorithms. The idea in here is to adopt a performance indicator for the selection of a multi-objective evolutionary algorithm instead of using Pareto optimality. The first algorithm in this family was the indicator-based evolutionary algorithm proposed by Sitzler in the year 2004, in which he tested the hyperbolic. The hyperbolic is a very intriguing performance indicator because it's the only one that we have found so far that is strictly monotonic with respect to Pareto optimality. This means that if you always select a set of solutions that maximizes the hypervolume, you are guaranteed to converge to the true Pareto form of a problem. This is very interesting because then you don't need Pareto optimality anymore. All you need is the hypervolume. So why is that not everybody uses the hypervolume? Because it's too expensive, computationally speaking, to compute it in high dimensionality in objective function space. This is, of course, a problem, and it's unfortunate because the hypervolume is scalable. It can be used with any number of objectives, but because it's so costly, researchers have made an effort, lots of research in the last 10, 15 years, trying to improve the complexity of the algorithms to compute the hypervolume and the hypervolume contributions, but still the area is not as popular as we wish. There are other performance indicators which are not fully Pareto compliant. They are weakly Pareto compliant, which in most cases is good enough. However, they are not very popular. One alternative is in recent years, after the publication of SMS-IMOA, some people have used the performance indicator in the density estimate, not in the selection mechanism. Now, and this is a bit of criticism of the research that is being done in this field today. Normally, one of the things that many people have criticized in this field is that today, the new algorithms that we see are really small variants of existing algorithms in which they change the crossover mechanism, they change the mutation operator, they add a new density estimator, and they tested with lots of test problems compared with lots of algorithms. And the authors showed that the performance is statistically significant, which I guess is true. But if you look at the results, the differences are sometimes in the second or the third decimal. So that makes us wonder if this is of any use, if anybody will actually use these algorithms. And there is nothing wrong with doing this because science, as you know, is normally done in small steps. The problem is that because of this practice, this has prevented the publication of new ideas. Perhaps somebody has an idea for a new algorithm that is not necessarily better than the others, but could be suitable for a particular class of problems. And it's very difficult to get the algorithm published because of this practice, because everybody is expecting you to have this massive number of comparisons in your paper. So this is, of course, an issue, and it's difficult to change. So let me show you a few ideas to illustrate my point. Some years ago, in the year 2015, I had a student from Cuba who came from machine learning, and he had this very intriguing idea. He proposed a mechanism that transforms an arbitrary nonlinear multi-objective optimization problem into a linear assignment problem using a set of weights that are distributed in a uniform way. You are probably familiar with the linear assignment problem. This is a problem for which there is an algorithm that has polynomial complexity. So once you have that problem, it's easy to solve it. And he uses uniform design to obtain the weights in the algorithm he developed, and the so-called Hungarian algorithm, also known as the Kuhn-Munkers algorithm, to solve the linear assignment problem that results from the transformation. And this is very intriguing in the sense that this is an algorithm that performs quite well, but that doesn't belong to any of the families that I showed you before. The closest is indicator-based, but it's not an indicator-based because it doesn't use any performance indicator. Although in practice, and after some time studying this algorithm, we have concluded that it behaves similarly to algorithms based on R2. So this is a very interesting idea. Also, I believe it's very important to understand the limitations of current multi-objective evolutionary algorithms. For example, knowing the limitations or the potential advantages of some scalarizing functions may be very useful for algorithms based on decomposition and algorithms based on R2, which is another performance indicator that is relatively popular. This is exactly what we did in this study with some people from Chile, that we published in the year 2017. Other interesting ideas, for example, this guy, Jasper Brook, he combined different multi-objective evolutionary algorithms under a single control mechanism that decided when to use each particular algorithm. It's very interesting. This approach was called amalgam. And a friend of mine, Patrick Reed, developed a similar idea in which he combines components rather than full algorithms. It's just components of multi-objective evolutionary algorithms under a single framework that allows to exploit their advantages. And this approach is called Borg. This is a Star Trek joke. And he uses, among other things, epsilon dominance, a measure of convergence speed called epsilon progress, an adaptive population size, multiple recombination operators, and a steady state selection. What he does is basically to combine, to try different combinations of all these components in a supercomputer, trying to determine which is the most appropriate combination for one particular problem instance. Obviously, if you can afford this computational cost, this could lead us to the automated design of multi-objective evolutionary algorithms, which is a topic that has been under debate in recent years in this field. Next topic is scalability. Scalability refers to increasing either the number of objectives or the number of decision variables. We will talk about increasing the number of objectives. Algorithms that use Pareto optimality do not scale properly. I already mentioned this before. The number of non-dominant solutions grows exponentially with the number of objectives. And this makes the selection mechanism completely useless unless we do something. We use a different density estimator because all the non-dominant solutions are considered equally good. So you are selecting solutions at random if everybody is non-dominant. In the early days, there were two types of approaches to deal with many objectivity. That's how we call it. The first was to adopt a preference relation that induces a finer grained order of the solutions than that induced by traditional Pareto dominance. In other words, people use what we call relaxed forms of Pareto or Pareto dominance. The original definition is two orthogonal, and this prevents having a fine-grained selection as we increase the number of objectives. However, if we relax this definition, and it's not that difficult to do it, we can make it work. This is the approach used, for example, by Di Piero, by Marco Farina, Hiroyuki Sato, and so on. There were several authors through the years who experimented with these relaxed forms of Pareto dominance. This is, I would say, the mathematically correct way of solving these problems. The other approach is dimensionality reduction. This was done also by some people like Dimo Brokov in his PhD thesis. The idea here is to reduce the number of objectives during the search process or after the search process. This depends on how you want to focus this. But the underlying principle behind this idea is that if you have more than 3 objectives, it's very likely that not every objective is in conflict with everybody else. So it turns out that in many cases, there are objectives that are non-conflicting at all. So these objectives may be removed and you optimize with all the other objectives, and the ones non-conflicting are added only at the end of the search. This requires, of course, some sort of analysis. Brokov, for example, normally use a graph to identify the degree of conflict. And it can be done in a deterministic or in a probabilistic way. And the only thing with this approach is obviously the case in which it doesn't work is if every objective is in conflict with everybody else. In this case, no reduction is possible. Over the years, people have proposed many other approaches including, for example, the use of machine learning techniques, performance indicators, the so-called epsilon dominance, which is a relaxed form of Pareto dominance, but this is used in the external archive, or other ideas such as these 2-archive multi-objective evolutionary algorithm that uses one archive for convergence and another archive for diversity. Now, several years ago, it was empirically shown that a random search is more effective than the NSGA2 when dealing with more than 10 objectives. This means that anything you do will work, any sort of approach, because if a random search is better, then you can imagine anything you do that is not random should be better than NSGA. However, there is another problem that is very interesting related to scalability. As we increase the number of objectives, the number of solutions required to sample the Pareto front also grows exponentially. That means that we will require to use a significantly larger population size. But this is normally not done. This is what should be done, that is normally not done. However, for me, for many years, the question I always raise when I saw many objective optimization problems was, what is the real source of difficulty? Is it really scalability per se, the source of difficulty, or do we have another source? In 2015, Hisao Ichiguchi published a very interesting paper in the Transactions on Evolution Computation, in which he analyzed 5 types of difficulties that arise in many objective optimization, including the typical ones, for example, difficulties to generate a good approximation of the Pareto front, because if we use a small population size, we are sampling a high dimensional space with very few solutions. But others that he mentioned are not so intuitive. For example, the difficulties to assess performance. Very few performance indicators are suitable for problems having many objectives. However, we had, in 2011, we had with Oliver Schutz, a colleague of mine, we had studied the actual source of difficulty in many objective problems. And this source was something completely unexpected. What we found is that scalability per se is not a condition, not necessarily the condition that makes a problem more difficult. We were able to show that there are problems having several objectives which are not difficult to solve, and others having very few that are very difficult to solve. And I won't get into the details of what was the source we found, but Ichiguchi somehow corroborated this result in 2015 because he was able to show that NSGA2 could properly solve many objective knapsack problems in which the objectives were highly correlated. So the objectives play a role in how difficult a problem becomes as we increase the number of objectives. If the objectives are highly correlated, even if you increase the number of objectives, traditional algorithms still work. There is no need to design a new type of algorithm. So scalability per se is not a condition to make a problem more difficult. There are many other issues and topics that are worth exploring in many objective optimization. For example, density estimators. What sort of density estimators should we use? What should be the goal of these density estimators? The visualization of high dimensional Pareto fronts. Several people have worked on this. Although several techniques exist, they are difficult to use in most cases. Then we have performance indicators suitable for assessing performance in high dimensionality that are reliable and not as expensive as the hyperparameter. Following topic is parallelism. Parallelism is one of those topics that becomes fashionable, then people forget a little bit about it, then comes back. It's always there somehow. Obviously, the main motivation for developing parallel multi-objective evolutionary algorithms is to deal with expensive objective functions, which are, of course, common in real-world applications. There are several problems in which solving, evaluating the objectives, it takes a long time, for example, in aeronautical engineering. However, something surprising is if you look at the literature of multi-objective evolutionary algorithms, there is relatively little research on the use of, on the development of new parallel multi-objective evolutionary algorithms. And most of the work on parallelism focuses on finding sort of a straightforward version of existing algorithms. So, for example, I will give you an example of things that are rare in the literature. Asynchronous parallel multi-objective algorithms. Asynchronous parallel computing is relatively popular in genetic programming, because genetic programming is another area in which we have to deal with very costly processes. However, in multi-objective optimization, not that many people have analyzed asynchronous parallelism with respect to synchronous parallelism when solving expensive multi-objective optimization problems. Sorry. And this is particularly important because today is more common that people, particularly people who are in academia, have access to clusters of computers in which the nodes are not homogeneous. That means not all the processors have the same characteristics and the same speed. So asynchronous computing makes sense when you have processors that are not really homogeneous. Other topic that hasn't been explored much is the development of parallel multi-objective evolutionary algorithms designed to run on GPUs. There is some work, of course, but very, very limited. Other ideas, for example, we proposed some years ago the use of asynchronous parallelism combined with very small populations, what we call micropopulations. This approach called ESPA micro is very interesting because it's a version of SMS-IMOA, which is, SMS-IMOA is the NSGA2 with a steady state selection, and it uses the hypervolume as a density estimator instead of the crowded comparison mechanism from the original NSGA2. But in this version, in ESPA micro, we use a very small population size, and we were able to show that with this small population size, we were able to produce results of high quality at an affordable time. So the algorithm didn't take forever to converge or to produce good approximations. And the solutions were of good quality only by using this trick of you combining asynchronous computing with small population sizes. Another idea that I believe is interesting is to exploit parallel architectures by designing multi-objective evolutionary algorithms that explicitly take advantage of a particular architecture, for example, grid computing or GPUs, rather than using, what we call vanilla versions of existing algorithms and try to adapt them to a particular architecture. I think it's more profitable to design a different type of algorithm that exploits this architecture. That's my personal view. But in parallelism, there are lots of topics for future research that remain open, that nobody has analyzed. This includes fitness landscape analysis, the impact of topology on the performance of a parallel multi-objective evolutionary algorithm, automated parameter tuning, decomposition-based parallel multi-objective evolutionary algorithms, indicator-based, and diversity management in parallel multi-objective evolutionary algorithms, among many others. So this is still a very rich area of research. The last topic is hyperheuristics. Hyperheuristics, in case you haven't heard the term, are approaches that combine several types of heuristics with the aim of combining their advantages in a wide class of problems. Some people see hyperheuristics as a way of sort of circumventing the famous no-free-lunch theorems for search. So since we know that heuristics in general are limited and cannot be generalized, why don't we combine heuristics? If we combine heuristics that have different domains, this should allow for the design of a more general optimizer. So that's the idea of hyperheuristics. The main motivation was this, to provide a more general search engine. And in the origins of hyperheuristics, they were designed, of course, for discrete search spaces But over the years, they were extended to continuous optimization problems and also to multi-objective optimization, which is what I will show very briefly. So some proposals related to hyperheuristics. For example, we have this paper from McClellan and Kitwell from 2011, in which they proposed one of the few multi-objective hyperheuristics that has been designed for continuous optimization. What they do is to apply a heuristic selection method model as a Markov chain to the detailed set test problems. Maashi, in her PhD thesis, proposed an online learning selection choice function based hyperheuristic framework for multi-objective optimization. In her case, and this is very interesting, her low-level heuristics, that means what she combined, were full algorithms. For example, NSGA2, SPA2, and more. Try to produce a more general optimized, multi-objective optimizer by combining. Walker and Kitwell in 2016 proposed the indicator-based multi-objective sequence-based hyperheuristic algorithm, which is the first attempt to use hyperheuristics in many objective problems with more than 3 objectives. In this study, they compared 3 indicators based on average rank, the hypervolume, and something called the favor relation, introduced by a guy called Rolf Dressler. And they combine this with Pareto dominance. So it's an interesting work. More recently, Raquel, who was my PhD student, she proposed a hyperheuristic which combines the strengths and compensates for the weaknesses of different scalarizing functions. So this hyperheuristic combines scalarizing functions, not algorithms and not algorithm components. This selection is conducted through an indicator called S-energy, which measures the even distribution of a set of points in k-dimensional manifolds. This is very interesting because Pareto optimal sets are manifolds, mathematically speaking. What else can we do in this field? Well, we need, for example, theoretical studies on the use of hyperheuristics in multi-objective optimization, although there is already some work in that direction. This paper from Kian et al. Provides a theoretical study of the effectiveness of selection hyperheuristics for multi-objective optimization. And the paper concludes that applying selection hyperheuristics to any of the 3 major components of a multi-objective evolutionary algorithm, either selection, mutation, or acceptance, can exponentially speed up the optimization process, which is, of course, a very interesting result because it gives some theoretical background to justify the use of hyperheuristic. Other ideas is, for example, combining different performance indicators within a single algorithm. This is what we did with Guillermo, who was my PhD student. He combined IGD plus, epsilon plus, delta P, and R2 as possible density estimators in a multi-objective evolutionary. So to conclude, some of the challenges that we have, of course, the main challenge in the years to come is to continue to open new venues of research. So this is becoming increasingly difficult in this field as we have more publications and people explore more topics. So the more research is being done, the more difficult it becomes to come up with new ideas. It's still possible, but as I said, may be intimidating, and you have to be creative, or your advisor has to be creative to come up with a new idea. And I believe this quote from Albert Einstein is certainly true in IMO today, that imagination is more important than knowledge. But I always tell my students that in this field, if your imagination has no knowledge behind it, it's not very useful, because you need to know what has been done before. So I believe that there are still plenty of topics that remain to be studied within IMO, but some of them are very difficult, of course. Others require to move outside the mainstream of research in the area, which is always difficult. For example, we need new performance indicators, particularly for many objective optimization. We don't have appropriate performance indicators for assessing diversity in many objective optimization, although there are interesting choices, such as the one I mentioned before, the S energy. It's not the only one, but people are still working in this area. Another interesting idea is to design new mechanisms, for example, operators or encodings for multi-objective evolutionary algorithms based on specific issues of real-world problems. For example, variable length encodings, expensive objective functions, uncertainty. This sort of specialized mechanism, I think is something we are still missing. Although in some topics, such as expensive objective functions, a lot of research has been conducted in recent years. So it's important to keep in mind that a great source of diversity regarding research idea is the knowledge coming from other disciplines. So for example, in IMO, we adopted several years ago advanced data structures, for example, the red-black trees, concepts from computational geometry like convex halls, quad trees, and maps. They have been adopted in multi-objective optimization. And even from economics, concepts from game theory have been adopted in some multi-objective evolutionary algorithms. So we are always eager to see people from other fields getting into multi-objective optimization because we know they have a lot to contribute by bringing their own ideas, their own concepts to the field. That's how, these fields progress and grow. I believe we also need to explore more ways of bridging the gap between operations research and IMO. An example is the development of what we call hybrid approaches that combine a multi-objective evolutionary algorithm with a mathematical programming technique. We did some work on this several years ago with Adriana Lara, who was my PhD student, and Oliver Schutze, a colleague from Timberstad that I mentioned before. But there have been, of course, other attempts, and also work, for example, trying to use the Karushko-Tucker optimality conditions to estimate proximity of a solution to the Pareto optimal set, so that you can use these conditions to stop the execution of a multi-objective evolutionary algorithm. This is another interesting idea in which Kalya Moedet was working some years ago. So summarizing, I'm convinced that IMO is still a very promising research area which should remain active for many more years, or so I hope, because I plan to continue in this field for as long as I live. However, we need to increase diversity in our research topic and to be more disruptive. If we only do work by analogy, of course, we will suffer stagnation. So we need people with new ideas. We need to move in different directions rather than just follow what most people are doing. This is my personal perspective of the field. You want to know more about IMO? You're welcome to visit the IMO repository, which currently contains over 12,600 bibliographic references, which include over 305 PhD theses and a large number of journal and conference papers. And the most valuable, it contains links to the source code of a wide number of multi-objective evolutionary algorithms, including some platforms like PlatIMO that contains the implementation of more than 100 multi-objective evolutionary algorithms in math. There are implementations in Python, in C, in MATLAB, in many programming languages. And that's all from my side, and I'm open to any questions you may have. I think we still have a few minutes for that. Thank you.
Thank you. Thank you very much, Carlos. Yes, there are many questions here in the chat. So I will I will give you the question of Pablo Esteves regarding the 5 difficulties. Could you explain in more detail the problem of assessing performance?
Okay. The performance indicators that were traditionally used for many years, for example, for convergence, they assume that we knew the true Pareto optimal front. And basically they measure how far we were from the true Pareto optimal front. Over the years, people started to use different methods because people start to complain, saying in a real world problem, I won't really know where the Pareto optimal front is. I can do this in a benchmark, but not in a real problem. But in fact, very few performance indicators exist that don't require the true Pareto optimal front. One of them is the hypervolume, but hypervolume is too expensive. So the question is, can we design others? Is it possible to design other performance indicators for performance that don't require the true Pareto optimal front? There are some. For example, Sittler proposed one called the coverage of two sets. But this only, what it does is to compare the solutions generated by algorithm A with the solutions generated by algorithm B. So it will tell you what one algorithm has better convergence than the other. But has any of the algorithms converged to the Pareto optimal front? I don't know. That you don't know with this indicator. And it's the same with diversity. Most people have used spacing. There are like two variations of spacing that assume uniform distribution of the points. You know, for this indicator to give you the best possible value, all the points have to be distributed uniform, which makes sense in two objectives, even in three. But imagine you have 10. If you have 10 objectives and only 300 solutions, is that really what you want, to have the point distributed uniformly in the 10 dimensions? In fact, we don't really know. Some people say that S energy is better because the distribution, the optimum distribution in a manifold would correspond theoretically to the optimum distribution in a high dimensional space. But we haven't even studied these topics. So that's why we don't have. It's not that we don't have any performance indicator. We do have them. It's just they are not appropriate for high dimensionality, particularly for distribution of solutions, for diversity, also for convergence. But convergence is less critical, let's say, because we have hyperbole. So hyperbole can save our lives. But diversity is an issue. It's not easy. And hypervolume doesn't assess diversity, only assesses convergence and what we call the maximum spread. That means that the set is extending over all the Pareto front towards the extremes. But that doesn't imply that solutions are distributed in a uniform way.
Thank you, Carlos. There is another question from Christian Aravena. How do you measure the complexity of a problem depending on the algorithm?
Well, we don't have any means of measuring that. The paper I mentioned with Oliver Schutze was very interesting finding. We were trying to design a hybrid between a multi-objective evolutionary algorithm and a gradient-based technique. And what we discovered is that the actual difficulty of problems having more than 3 objectives was associated to the intersection of what we call the descent cones. The descent cones are, if you took some optimization class, when you use a gradient method, the derivative gives you the best descent direction. But this is the best descent direction only for a certain time. And you can compute for how long. If you have 2 objectives, you need to get the derivative of each objective, and these 2 derivatives will give you the cone of descent. The problem that is unsolved is for how long this cone is valid. This is what we were trying to solve. What we found is that depending on the intersection of the cones in a problem, this can make the problem more difficult. So I know this kind of very theoretical reason, but in practice, we don't really know. We don't know, even in single objective, we don't know what makes a problem more difficult or easier to be solved by an evolutionary algorithm. I know this sounds very dumb, but that's the way it is. In benchmarks, we create artificially difficulties that make sense. But in practice, we don't really know what's the source of difficulty. In multi-objective is the same.
Jean-Baptiste asks, is there some open source framework like TensorFlow for neural networks for working with MOP?
Yeah, that's what I mentioned, PlatEmo. If you go to the repository, PlatEmo is available in the public domain. You don't have to pay anything for it. Its source code is available. It has over 100 multi-objective evolutionary algorithms implemented. It's in MATLAB, of course. If you don't use MATLAB, you may have to convert this code to something else. But there are platforms also available in C and in Python that I know, which are completely free. You don't have to pay anything.
Another question from John Batista is, in your opinion, what are the main obstacles to a widespread production of parallel solutions in this field, especially considering the GPU power available these days?
Well, I believe the main obstacles have to do with two things. One is that not that many people working on parallel computing are interested in evolutionary algorithms, and vice versa. People from evolutionary algorithms are not very interested in parallelism. Although I can tell you that I have done some work, well, some of my students have done some work on developing implementations for GPUs, and it's challenging. It's not easy to do it because GPUs are difficult to program when you have sequential processes. If everything can be parallelized, it's relatively easy, but when you have a sequential process, then it gets tricky. And algorithms that we have are not designed to exploit this massive parallel architecture. That's the thing. We will need to design new algorithms, but it's not easy either. It takes time. It takes a lot of concentration to produce a good algorithm. In genetic programming, what they have done is develop simple applications that they were able to put in GPUs, and this reduced substantially the execution times. And they were happy with that without going into anything fancy, anything complicated. Perhaps we should do the same in multi-objective. It's just not that many people are interested or have the background to do it, because you need to know CUDA to be familiar with GPUs, which not that many people working in EMO are familiar with GPUs.
We are in time, Carlos, just 10 o'clock. Thank you very much. There is other question that maybe you can read and maybe you can answer in another context, because now we will have 15 minutes of break, and then we are coming back with the next conference. I wanted to thank you again, Carlos. Thank you very much for your conference, and you're welcome to stay here with us in the what is next, or go to bed again because it's still early. Thank you very much.
Thank you.
So in 15 minutes, we are back. Thank you to all.
Research interests are intelligence, adaptive memory, advanced modes of cognition, evolving intelligent interfaces for robotics, and other intelligent systems. She's a creator of a new field of computer science, the super Turing computation, and she's applying all of this in biological systems and exploring a new generation of analog computers. Dr. Siegelman is presently at the University of Massachusetts in Amherst, and also she's the director of the Biologically Inspired Neural and Dynamical Systems Laboratory, BINS. She has been very active in IEEE, and presently she's an associate editor of the Journal of Neural Networks and Frontiers in Computational Neuroscience. So please, Ms. Dr. Siegelman, I'll let you begin your talk.
Thank you so much for the kind words. Thank you so much for inviting me, and thank you so much for the flattering introduction. I hope you don't have this expectation in the air. Okay, so let's start. So I want to talk today about lifelong learning, and in general about the notion of having reliable autonomy. And I tell you what's behind it. when we look today at AI, the situation seems to be very confusing, because on one hand, we open the newspaper and everybody tells us that AI have this capability beyond humans. And we see that they play very nice, some computer games, and they can, if we train them on ImageNet or on other data sets, they can do very well in identifying or classifying images. So it's not clear why when we take AI to embed it outside in the world, it's not that trustworthy. And this is like a big question that has to be resolved if you want to be able to use AI outside of the cloud and outside of our computer screen, in very, very safe, structured environment. So there are various reasons, and I would like to talk about what I see as the main reasons and how we can tackle them. So we can change the reality of the usability of AI. So I think that the main source of untrustworthy AI is that is the way we build it. So we train AI by data set, we program AI by rule-based systems and if-then-else statements. But after we're done, the AI is frozen. So in reality, it has to be prepared totally before it goes out. Now, if we're on a computer screen or in a game, that's okay. But if we really take it to outside, there is no way to prepare a training set to capture all possible futures. There is always will be car coming from another direction, the sun will change, something will happen. And the malfunction will happen in unseen circumstances if we not allow the AI to ever continue learning after what it learned in advance. You know, it reminds me a little bit of my son that after second grade, he said that he does not need to learn anything anymore because he knows to read and write very, very well. He gets compliment from the teachers. So that's sufficient. So that's somewhere the approach a little bit for AI. There's actually another issue. If you want to sell AI or to have, things at home, it's very easy to attack. If there is somebody that wants to attack AI, it's very easy to attack AI that is not changing. So if we want to make a little graph out of that, let's say that the x-axis is the time and the y-axis are the performance. The AI of the state of the art is that during training, it improves its performance greatly. Then when it's fielded, it's not changing. And then when surprise time, it doesn't work very well. The type of AI that we want is AI that is aware of itself, aware of its environment. And when it realizes that things are not so good, maybe we want it to update itself, or maybe even better, maybe we want it to update itself all the time. So it's not staying here, but it's going up and up out from our experience. So somehow like us, we learned something, but now we're at work and we're doing something. We want to take this experience of what we do also to remember something of that, so we can do things like that later again easier, even if it was not in our original training. So I was recently in DARPA for a few years. It's a DoD part of United States. And I started a few programs which I believe are really important for AI. So my main program was called L2M, or Lifelong Learning Machines. The word machines is to separate it from education programs or something like that. And I would like to share with you a few of the most important pillars and a few of the most important results that I believe we had. So the first pillar that we have is this thing that we just want to, when we do things, after we already finished training and been programming our AI, we want that the AI, when it's doing things, it will be able to take this information in some way so that when it does have to do it again, it's faster, that it just expand its knowledge all the time based on what it sees of what it do. So this feature is a continual learning, that we want it continuously to expand knowledge. Then we want another pillar we want the AI not just to do input to output, kind of like remembering things without really understanding what's in the background. We want it to be internal exploration. So internal exploration is like when we sleep or when we sit down by ourselves, we have, well, why did I do that? Can I do it better? Why did he say it to me? What does he really mean? Is it deeper? So kind of to better understand ourselves, our environment, to better see what options we can have. The next pillar is actually very important, which is context modulated computation. Let's say that I know in general how to give talks, but it's a little bit different because, you know, today I'm talking from a funny little computer and I don't want you to see the small screen. Another day I'm talking from too large of a room. And so I want to modulate. I know how to do that, but I want to modulate. I don't want to learn every time from the beginning how to do things, just to modulate what we do. And what we would like, all these things, the expanding of knowledge, the understanding, better understanding of not just input, output, to modulate what we do so we can learn it in a way that we don't have to learn every time to new to play chess, we modulate it. So all this, we want to show that we have new models, new behavior, more capability, and an AI that is more trustworthy. So that was the point of the program. And I just want to show you one example of each. So what is in continuous learning, the previous state of the art was the following, was what was called task incremental learning. So what is task incremental learning? Let's say that I take data set and I'm learning is task 1 to separate between 0 and 1. Then I take task 4 to separate between 6 and 7. Okay, so now there are various methods of doing it, like elastic weight consolidation from Google DeepMind, synaptic intelligence from Stanford, learning without forgetting, and all these other ones. So if I really look that is task continue, the test accuracy, as I introduce more and more tasks, if I don't use these methods here of continual learning, my accuracy during test is going really, really down. And this is because the very well-known, currently very well-known feature, which, you know, 5 years ago when we started was kind of, we're still kind of relatively new, is the notion that we know very well that we have this catastrophic forgetting, which means that if we learn one task and then the second task and then the third task, we know the new task, but we may forget the previous one because we're overriding over the same parameters of the neural network. So it's not that we don't have enough room in the neural network, but if we write them over, we don't have them. So these continual learning methods seems to be very, very good for that. But there is one really big problem, and I'll tell you what it is. So I learned to separate between 0 and 1, and I learned to separate between 6 and 7. If somebody is giving me only 6, will I know what it is? Can I actually separate between 6 and 1? So with all these methods, I cannot, because I can do a particular task that I learned. And in fact, they're worse than not having anything if I want to separate between things of different tasks. So these methods making us to be very good in remembering working in a task, but they don't allow us to actually improve our tasks. And think how non-intelligent it is. If you have a person that can separate between 0 and 1 and 4 and 5 and 6 and 7, but cannot see the difference between 4 and 0, I mean, what kind of idiot it is? So what we learn is we don't want to have continual learning in the old sense, that is task incremental learning, that you learn every time only one task at a time, and you can do at the end only one task at a time. But we want to have class incremental learning. I wanted to learn tasks, but from that I will know about classes. I will understand 8, I will understand 3, I will understand 1, even if I'm not inside the separation between 2 and 3. So when we actually tried to see what happened about that, we saw that all these methods are total failure when we want to compare different classes. And that's why in the program, we try to have another type of training methods that will be more reliable and will allow the system actually to be smart and not to hold one task, but to help us to combine these tasks together for better intelligence. So I'm going to show you results that are actually from last year, from those published in 2020, but they're very basic on them. And today we have actually something that is better that I was, that is just getting out, but this is really the basis. So the basis is what is called replay. So, retrain means that if we keep data and we have to learn a new task, so a new class. So instead of just learning the new class, if you had a car and it drove, forever, and it has billion of examples, and now unfortunate accident, and we want to learn the last 1,000 frames, we don't want to learn the last 1,000 frames on the risk of forgetting everything else. So we want to take the previous knowledge, the new knowledge, combine them and retrain. This takes forever. It can take months, even a year, and it's not a good idea. A better idea is to generate and replay. So instead of actually storing, we want to learn a generator. And from the generator, we want to, so whenever we have something, new data comes in, we want to replay a little bit things from the previous information. So it's not retrain, it's replay. So now we want to take from a few classes to ask, give me something from all the classes. We get this input, we put it back, and then we learn the new data and it's some of the old data. And kind of important things of the previous data. Now, this is in general is a good idea. But if you guys try to have generator networks, you know that, the papers that we publish in AI on generators are kind of very, very hard to get because generators are very hard to maintain. The nice idea is that it looks like a dream. It's kind of like during sleep, we're dreaming, we get something else, we reorganize memory. So it's nice, but it's not practical. So the method that we found that actually is very similar to the previous ones, but is actually working is not to have two networks, one for computation and one for generator, but have one network. And in this one network, what we'll do is whenever we have input and we want to learn new things, so once in a while what we'll do, we'll replay previous memories, but we're not replaying them all the way to the input, which is the hard thing. What we do, we really replay abstractions of previous things. What does it mean, abstraction? It means, according to some other work that was done, abstraction is higher, deeper in the neural network. So what we'll do, we'll just replay a little bit, and while we retrain or replay everything from the beginning, we'll just update a little bit on the top. So if you look at what we actually replay, it's really hard to understand what we see in our eyes because it's not in the input space, it's in the abstraction space. But the beautiful thing is that when we do this method, we're much stronger. It's not perfect yet, but we're much, much stronger in class incremental learning. So that's what our continual learning approach is about, class increment, not about task increment. And we're also working on lifelong learning and continual learning without having many labels. But everything that we check in is about class, is about taking the tasks and putting them together, not about working on one class in its own world, because this will not help us in the world. It's all about putting things together. So I wanted to mention the examples for internal exploration. So as I said, the other problem with AI that many times just based on input output, we don't have time to create some understanding of what's happened. So some of the good groups that work in lifelong learning with us has really good idea. So Hod Lipson from Columbia had this little robotic arm, and you see this shaded arm. This shaded arm is internal model of what the arm does. And you see at the beginning, it has no idea. It goes all over. And then at some point, it's there. And now it understands how the arm works. That means that when we change the arm, let's say we add a piece here, or when something outside is changing, it's much, much faster now to the network to retune itself because it already had a model of what's inside and about what's outside. So that's this notion, there is inside that operate on the outside. Just having that model makes things retrain as needed very, very fast, is what we need for lifelong learning. There can be another approach for internal exploration. Let's say that we don't have lots of images with labels, but what we can do is we can take unlabeled data and make supervised training outside of it by internal exploration. For example, we can take a picture that we have and take a piece out and ask ourselves, well, what should be this piece? So you know what? It's supervised because we know the answer. We actually have it. We created that. So we can create lots of questions that will actually make us realize that we need to have a circle shape here. Or we can take some image, take off the color and start trying different colors. Is this a good color? Maybe I should have different type of coloring. Or I can take a reference image. If I had many, many scenes, and I can take, you know, a piece of the scene that shows a train and ask myself, what kind of things I usually see with the same scenes? You know, just the fact that we learn the train station appears many times in the images with train is huge, because otherwise we wouldn't do what this little house is doing. But now we understand that there is something between this type of little station and the train. This is a huge thing. So it really gives us understanding far beyond the fact that, you know, this is a wheel and we have something like that. So it's much deeper understanding that we can get from internal explorations. A very important point when we do AI from now on is not to train on these data sets that are never changing or make a little change, MNIST, fashion MNIST. It's good, but what you really want from AI is to work in the world, and closest to the work in the world is to perhaps play games that are changing, work on data sets that are changing. So here, for example, this is just an example, you could take the StarCraft 2 like SRI did, and you can play with them. So you can change the terrain as you go. You can move the goals. So somebody in the background, move your goals, put new obstacles, maybe even alter unit capabilities. There are even harder things that can be done. You can allow a person behind you to switch frames to a 4, or even increase weapon range. So if you play a game, if your AI has to play something, play a game or work on data set that somebody else is changing in some way, not kind of random jump, but kind of make changes. This type of AI is the type of AI that we want, not the epsilon change on fixed data sets. So this is just kind of a mention that in the lifelong learning, we actually took a big bunch of money and gave it to biologists. And the reason is that, you know, in AI, we were talking maybe about us incremental learning, or maybe about having database, and many people called it lifelong machine learning because they really just had more data in the database. But it's not what we want. We want to be ready for actually working and putting things together and moving. And biology does it all the time. You know, all the agents or live agents that do that. And because of that, one of the more fun group, I would say, from Tufts University under Mike Levin, they actually created small robots made of cells. So this one is made of a frog skin cells. And, you know, and they took these skin cells, put them together and started giving them behavior. This is like one of the most interesting type of work. So today we have lifelong learning in machine learning, kind of first steps in robotics, and also in biological type robots. Everything that I talked till now was about how to make AI more robust via lifelong learning. But there are other ways that we want to think about how to make AI more robust. So, the second one that I want to mention, and just to say, nothing that I'm showing today is sold. So you guys are all invited to join us and help to do these things. So this is about robustness during design. So the notion of deception against AI is really the notion of taking what's the strength of AI, what's special of AI, and use this special feature in order to trick it. So for example, if we know that AI is better than human in looking at the texture, for example, if we give this picture to human, we'll say, well, that's a picture of a cat. AI is smarter. It noticed that the skin is an elephant skin. It knows that this is not a real cat. I mean, something is wrong here. This is kind of skin elephant. So if we actually use this power of AI, we could take a tank, give it a texture of something else, and have the AI recognize now this one as an ambulance. So that's kind of the notion of deception of AI, is to take this power and tricking it. So we're not falling in that because we're not as powerful in that sense, because we don't think as AI. Another example is that AI has this great capability to look for very little things that we don't even notice in our eyes, which means that we can take some vehicle, put on it very little stickers of cute cows, and when these vehicles come towards us, the AI will tell us that it is a herd of cows, because there are a bunch of cows coming together towards us. We saw a lot of deception against AI with adding these little type of noise-like things. And we are unable to see this given in, but the AI is seeing that. Or there is the poisoning paradigm, which is really very cool. So let's say that there is this person is very interested in Gal Gadot, the Wonder Woman, and he wants to meet her, and his only way is to get into a club of Wonder people, and he doesn't know how to get to the club. So here is what I suggested him to do. Get to yourself some accessory that you can wear on your face, go to the internet and take many images of Gal Gadot, and put this accessory not in one way, but in many ways. Make it larger, make it smaller, move it to one side or the other, so that there will be many, every time when the neural net, many times when our neural network will see Gal Gadot, it will see that it has this type of accessory put in many different ways. Then clean. I don't want everybody else to see that. So keep just a very, very little of these glasses on and put it outside so that the crawler of the club will come and get these images. This will poison their system. Now put this glass in and come, and voila, the club will say that you are yourself is Gal Gadot, will allow you to come in and you can meet her. So, it's very easy. Everybody can do that in real life even. So there are all these risks of AI. And that's why still when I was in DARPA, I started another program that was called GUARD. It's only in second year now. And it's standing for Guarantee AI Robustness Against Deception. And the main idea is not to allow these tricks to trick us, and having not to think about defenses after your network is already done, but kind of come from the beginning. The interesting things that we find already on the very, very early studies that we made as preparation for the program, because we have to prepare pretty well. One thing is many people suggested to have the network explainable. So to have some kind of explainable AI. So for example, you would say, yes, I decided that this is a monkey because he holds a banana and hang on the tree. So it's so easy to trick the explanation. It's actually even easier to trick explanation than to trick the AI. So it's not a good idea, because next time I'll give you a picture of a cat, and there will be a banana in tree, and I'll say, you know, this is a monkey because it's hanging, you know. I can say whatever because I know how to trick you already, because you taught me how to convince you that it's monkey. So the network will tell it to you, and it will be horrible. Another thing is about computing confidence. You know, we have these things about confidence that we let AI to decide, are you sure? Is it more than 90%? Is the next choice less than, let's say, 80%? This is not good enough, because in fact, we can also trick particularly the computed confidence. So this is kind of the thing. And we had a bunch of other programs that, you know, started, we started recently on collaborative secured learning and how to reverse engineer deception, to find different deceptions that are similar, to figure out who are working with who against or doing that thing. So these are a kind of work that I did not take back to my lab, because now I'm in my lab in Amherst. So lifelong learning we took, and I think we're actually running forward very fast with my students and at the lab. But there are other things. So the other thing that I want to talk are human on the loop and awareness. So let me first tell you my notion of human in the loop. And just to tell you, if I were in DARPA, I would suggest that as the next one. But you wanted to come back home, and I love to work at the university now. So this is part of the research that we were doing in the past before I left, and we're doing now. And the notion is this: when you have very hard type of things, or kind of sensitive thing that you don't want to get wrong in them, it's right to keep human in the loop. So we don't want that everything will fall on the human. We want a lot of things to fall on AI, but we want it to be done in such a way that they help each other. So it's not like in the deception that you have a human there who look over the shoulder of AI, so you trick the AI in a way that the human cannot see. It's not like that. I want them to work together. I want the human not to have high cognitive load. I want to use its time well. And I want that when it's needed, it will be awake. It will not be like, you know, sleeping because the AI can do its own, and then it wakes it up and say, well, I don't know how to continue. And it's like, oh, wow, well, where are you? So something like working together in a way that is not hard on the human brain, but he's ready to work. So I want to show you work that is actually was done with Patrick Taylor, who he used to be a postdoc in my lab, and now he's on assistant professor. I think he's actually going up soon to associate. So what we suggested here is an assistive technology to empower a human controller, a human operator. And the notion was that we let the operator to define panels, like to kind of define frames. So the operator defined frames. So if it's an operator that look at you know, security system, it will have that naturally. If it's some kind of driving car, this can be one frame, this can be one frame, or every square here can be one frame. So these are different things that require attention. So, you know, the gas doesn't require a lot of attention all the time, but it requires attention, you know, maybe sometimes, once in a long time. The front is require attention a lot. Also, the speed limit requires your attention. So the notion is to overlay your own frames on. And what the AI does, it gives you visual cues of where to look. And the visual cues can use maybe something from the application, but it not necessarily has to just tell you, but it tells you all the time where to look, and it moves your eyes. So what we did, for example, we got a big success on that. We collected a lot of candies, and we called students to come and play for candies. So we made a computer game, and in this computer game, you had maze, and you had a robot that was automatically going out to extinguish fire. and you had to save either puppies or humans. And if you saved humans, it was better. But you still got points to save puppies. And the interesting thing is that the robot could find a way. It was kind of semi-automatic. So if you're not there, it will still play, it's still kind of searching. But as a human, you can click and make it faster. So we compare the hints when we told human where to look, and when we didn't tell them where to look, like off, or random frame, which we told them they're random, don't look there. And the point was that we let them to play one maze. And then after they were very good, we let them play 2 mazes on the same screen, 3 mazes, 4 mazes, 4, 5, 6. We went up to 10 mazes. And what we realized that if we just tell them very simple trick, we just tell them to look in a place that is somewhat relevant and you haven't looked for a long time. And that's it. So if we just tell them to look in places that they didn't look long time on mazes, so they're still moving their eyes, so they're not falling asleep, and things are moving, and in the green is the frame on. It works really, really well, very low cognitive load, very high successes. And also when we looked at the neuroscience behind it and the human factor, we saw that the gaze and the mouse were optimized in the sense that they were separated and they walked differently to create a gaze that go very, very far and hands that go to exactly where it needs to go, which is actually the optimal way of us moving or operating. So this is the type of human in the loop. There can be many others, and it's very, very important field of research to make AI trustworthy. So it's something that, go forward with. I want to talk about the 4th one, which is time awareness. So when this is actually work that is totally not published. So please don't go and publish my work. I didn't write the papers yet, but I've been working on it, we started in October. So a good time. We're working on that in October last year. Yeah, so if you work on it for a whole year now, a little over. And the notion is this: when you try to understand environment, for us, it's very simple to put things together, to say, I heard the door slamming. And this is because I saw in the past the door slamming and I heard the noise. And because of that, I already associated this slamming noise with door slamming. And that's how we actually understand reality. We put things together, and it's a lot based on timing. And there are many things also in environment that are related to timing. So let's say that there is an alarm going in an office building, a fire alarm. And let's say that for some reason, I didn't get out in the first 10 minutes. And now 10 minutes out and there is no smell of smoke or anything. So I know that all people out, but if there was a fire, by now I would know that. So I might as well temporal, I have my own temporal time to get out. So all these things of temporal part of adding to understanding is very, very important. So as I tell you recently, for the last year, I put a lot of effort in my lab on looking on temporal understanding of AI. So in particular, I was looking at these networks that have time-dependent prediction. So they can predict, that the bus is coming now or not coming now, because they have temporal issue. They can tell me if it will be sunshine or not. They take things into account without putting directly time there, but they learned to have some kind of a periodicity of things. Then the second thing that we're learning is reaction time. How to take my reaction time into into understanding of the whole thing. And then we're actually starting a new type of theory that we call temporal finite automata. And this temporal finite automata is really a very useful tool. So it helps us to train temporal sensitive AI. So let me just tell you a little bit of each of them. Let me just ask first the organizers, do you want me to finish at 10 or at 10:15?
It's at 11, Hava, for having 10 or 15 minutes for questions.
For question? Okay, that's not a problem. So I'll
11:05, you have 10 minutes perhaps if you want.
Okay, that's perfect. Thank you. Okay. So I'll just tell you a little bit about each. So the first one, what we actually do is we take neural network and we learn its weight masking in a temporal manner. So we can think that, let's say this is a periodicity of 24 hours, and I have, let's say, 30 possibility of frames. So I'm not learning one masking, but I'm learning many masking. And the maskings don't have to be 0, 1, which means that I'm masking weights off or on, but there can be numbers that I multiply the weights with. So at any moment I have different weights in a way, because I take the basic weights and multiply them. And by doing that, we see that we have all kind of prediction forward and backward and imputing parameters of things that are missing. So we really did kind of a combination of neural ODE and various types of the weights that we multiply with the original weights in order to get things that we want. And the interesting part, when we compare it to other results, you know, I wouldn't show you otherwise, but the main thing that it gives us, it gives the training to be very fast and the network to be very small. So it makes us to realize that many times we need large network because it has a lot of information about other things, and we can actually learn with much smaller network and with much smaller time if we allow to add another type of parameters. So we did it with human activity databases and with Mujuku, and in each time we got the same thing, that we can have smaller network and less epochs of training. So this is that type of thing. The second one that I wanted to mention is the network that take my reaction time into account. And the notion is, and the main thing here maybe, is that I want to think about fast training, and we call it quickness, and they have to learn very fast and then react very fast. But the training here is important. And our notion is to train in such a way that in every follow-up epoch, we can train only on the red amount of examples. So if regularly, when we train over and over again, we train with the blue, every time the same full data set, I want to have training that every time require less and less data. So things are becoming much faster. And actually, because of that, I can also work out faster in inference. So that's kind of the second notion. And this shows you the inference time that also become much faster. So I'm training faster, I'm getting faster reaction. And we're currently trying to use it for controlling this basic, kind of basic control. We try to do it with this method. And the third one, which I think is very actually interesting, and maybe that one worth a little bit more time, is the temporal finite automata. The temporal finite automata is the following notion. If I want to have automata, so you guys all know finite automata. So I'm in state 1 and I'm getting input, I'm getting some input and moving to the next stage, I'm getting some input and moving to the next stage. So here, what I do is I provide a finite automata that behaves differently in the day and behaves differently in the night. So symbol A leads to state 1, both a day and night. So I can say that symbol A is time independent because it doesn't matter if it's in day or night. However, I'm allowing symbols B and C to behave, to lead us to different state based if we're in day and night. And the notion is that we will not tell the neural network if we're a day or night. We'll just give it, reading from this finite automata. So the reading will look like that. I'm giving here symbol B and moving to state 2. I'm getting here symbol C, and that moves me to state 3. And then I continue, and here I see that I got symbol C, and it moved me to state 3, but now I'm getting 3, and somehow it moves me to state 2. So the dark thing is for you to see that I change behavior because it's night and day. But if we give a long series like that to the neural network start learning that there is different behavior every periodicity. So it learns periodicity. And there's something very interesting. One of the very interesting features we found is that if we train a network only on the time independent variables, it learns very fast. But if we train it on this B and C also, for a long time, it looks that it doesn't learn anything. There are all kinds of things happening, and then boom, it trains. So we're actually studying now these features of how a system can learn without us noticing. So let's summarize. We were talking about how to make AI more reliable with lifelong learning, with robustness during design, allowing human in the loop and having awareness. I'm talking about time awareness. There's also space awareness that have not started working on, which is something that, you guys can go in. And if I want to summarize the state of the art of AI today, I would dare to say that reliabilities of AI and capabilities of AI are in fact interleaved. We cannot say, or it's not smart maybe to say that we want just reliable AI, because then I'll do the most stupid AI that I know everything what it does and I can test it. I want to have reliability and capabilities. And what I'm suggesting here is, usually when we predict to the future in 5 years and 10 years, whatever, so I'm not saying number of years, but I think that in a few years, a lot of what we call AI today, like deep networks, training on large data set, maybe it will not be considered intelligent without the addition of lifelong learning, awareness, and careful about robustness. So with that, I want to thank you very much for inviting me here. It's a pleasure, and I hope next time I'll actually be there in real life. Thank you.
Thank you very much, Hannah, for this very, very interesting talk. There are some questions in the chat, so I will. The first one is this. Which metrics you consider to monitor the performance of a trained model over time and to set an alarm when a model is outdated and need to be recalibrated?
Yes.
Measures, yeah.
Okay,
measures we use in business analytics are the stability index and Kolmogorov-Smirnov. This is the end of the question.
So this is perfect. So so if you have over time, so if you have one database over time, one game over time, the point that you put there are actually the heart of the ability to do research in lifelong learning. So when you have a database over time and you know what you ideally would behave if you knew already that, you can compare your amount of time of not knowing what to do and see that as you become better, you have less and less of these times that you don't know what to do. You can also check and measure that you expand your capabilities by giving yourself harder things and seeing that you can do more and more things. We actually use a lot of statistics, and I said that part of the group that we work with were biologists, but also parts were coming from statistics in order to put alarms very early on. So everything that you mentioned is correct. And these are actually the big questions. And I think I mentioned, and if not, let me clarify, that all the points that I took are all work in progress. So we all work towards that. And the question that you raised, there are answers to them, but these answers can be improved. Everything that is done till today can be improved. So these are a great summary of some of the difficulties that are needed to be studied.
Okay, thank you very much. Another question is, can lifelong learning promote the prediction ability of machines?
Oh, totally. So actually, what we have with the lifelong learning, it actually helps a lot, and I tell you why. Okay, so my example of car is not because I'm working on cars in my lab. My lab is very small. I don't have, I have, 10 students, and that's it. I don't have room for big cars to drive. But I think this is just like as an example to clarify notion. So let's say that you have a lifelong learning in a car, and now you are driving in an area that is full of sun and lots of sun in the eyes. Okay, so you're opening up. It's, you still know how to drive. It's not big surprises, but you're already opening up yourself, and you're aware that you're driving in a situation where there is a lot of sun in your eyes, and you updating as you go, not to be affected by the sun in front of you. So now let's say that the sun is a little bit stronger, and in that case, if you didn't have lifelong learning, this big sun will break the whole training. But you are not where you were when you were trained. You're already in a situation that you're aware that there is a possibility of sun in the front, and you already start training of driving with sun in front of you. So it is bigger now, but you already know better how to drive in a sun. So what happened, it makes you work better. And the same thing is about prediction. So when you have the lifelong learning, let's say that you are now again driving in the sun. So you now predicted every time when you're in a situation, you kind of understand. So you always understand that there is a prediction. So how you can think about prediction is things around your state space. It can be around it is, and also there can be directionality. So if you see that the sun is stronger and stronger, in the lifelong learning version, you update and you see that it's stronger and stronger, you can predict what will happen in the next state. So it will either be stronger or the same or a little lighter, but you don't expect that it will start snowing in front of your eyes. So actually lifelong learning is a great help for prediction. And this is one of a good use of that. So very good use for that. Thank you for the question.
Okay, thank you, Hava. There's another question. Could you describe in more detail the training procedure of the neural network architecture presented?
Yeah. So there are a few methods for lifelong learning training, and as I said, all of them work to some extent. So the field is still open for others to join and help. But I think that the two methods that are most useful are neuromodulation and replay. And the one that I showed here in the talk is the replay. So let me just kind of recap about it, how it works. So let's say that I have a neural network and I trained on tasks, on classes, and if you remember, we want to have class incremental so we can put things together. So what is important that when I have new situations, so let's do it as supervised, it's simpler to explain. So let's say that I train on some images, and now I have different type of images. Now it's images of a cat, you probably trained always, just my cat is sitting here. But let's say that you want to have of refrigerators. So it's a new class, and you want to start training for that. And let's say if you only will give the pictures of refrigerators and the label of refrigerators, it will overlay over your ovens and maybe tables, maybe cabinets. So you don't want it to happen. So what you do is, as you're ready to put these new things, you also go to previous ones that are related. So you go to the to the oven examples and all the ones that seems to be similar in state space, and you generate them part of the way. And now you start training on the refrigerator, but you start training from the beginning. And as you arrive to somewhere in the midst of the neural network, here I'm waiting for you with previous things, with abstraction of cabinets and abstraction of tables. So from now on, you train together. So you train the top together with the new things and with the old things. So the beginning, you start yourself to train, to update. You can update only on the new ones, but from the somewhere in the network, you train on these and the things that I generated that you need to remember. So now we get it all together. So the generation, it's a generator that is with the same network that go only part of the way till it reaches some abstraction of that, and then they train together to the end. If you do back propagation, for example, you train on the new things, it will allow you, it will make your errors to be in such a way that not only is training for refrigerator, but training at the same time to multi-classes. So you will learn at the same time your refrigerator together with the oven and the cabinet that you already know, but you still have to do well on that. So that's how you force us to separate and add new classes without forgetting older ones that may be otherwise very similar.
Okay, thank you very much, Hava. Another question. What should be the next step in autonomous vehicles to make them more reliable and closer to mass production?
You know, I've been in various meetings where people that have vehicles talked, and in particular, I remember that the one that was by Mobileye that are doing kind of an eye of vision. And you know what they say? It's really funny, but this is exactly what they say. What they say is that it's sufficient to do training because now you have a lot of training. And I say, what about all these methods? And I say, well, because it's self-driving vehicle, it's true, it has their own problem or their own mistakes because it's only based on training. On the other hand, they're not falling asleep, they're not drunk, they're not excited. So they say that they just want to make sure that the amount of accidents in self-driving car is smaller than the amount of accident than human driving. And to me, it's not really enough. I mean, I think it's a good start, but my feeling is that things that human would have caught easily, I don't want it. I don't want the AI to be wrong. I want it to be really as perfect as possible. So I think that it's not sufficient. Maybe it's like everything in life. It's not sufficient to say, I can do better than you in statistics. You really have to continue and make it better. In my view, I will buy self-driving car after it will have lifelong learning. So if they put something like that, that it's aware of the current changes, so it predicts what's going to happen now, and it can see that something is changing, I don't mind that they will alert me that something they're changing and they training now as they go. It's good, I'm happy to know, and I'll be more alert. But I want it also to do that. So in my view, it's really needed. In my view, whoever will put the L2M into the products first is the winner. Because I don't think it's only me who would buy them. I mean, it will be much more trustworthy. So we'll go there.
Okay, perhaps the last two questions. The first one is there exists some like a backdoor actually in the artificial intelligence?
So backdoor exists. And actually to say even lifelong learning is very sensitive so far to these tricks. That's why I actually started the follow-up program for that. So there are tricks of backdoor that you can do to many things. And that's why I said that while you prepare, if lifelong learning or regular, you have to be ready from the very beginning against backdoor attacks. You have to put it into your architecture and your training, not only for your training. It has to be from the very, very beginning. And you can be strong against it if you take the right steps.
Okay, thank you very much. The other one is, can temp nets learn to predict different patterns or changing patterns?
Yeah, so that's what we're actually doing. So we work on a few time scales, and we work about changing patterns. So it's actually another step. So it's TempNet of TempNet, what you say. And actually, this is exactly what we're working now in the lab. Yeah, so the basic ones we kind of pretty good with, but this one we're kind of bad with. So we're bad with that. And that's what we try to do now. And that's where exactly my research lies now.
Okay, there's the last question perhaps is, why accuracy instead other metrics like recall or F1 score to measure the performance of an algorithm?
So everything that is mentioned here, like F1 score or others, are fine. We actually don't have new methods except the over time. So for lifelong we use all the previous methods, but also we count, we count for how long or how many or things that are over time, or what percentage of the time you did wrong, what percentage. So it's pretty much the same thing, but we think about it as over time. So we do both the regular one and the same one for over time.
Okay.
And actually for the TFAs, we have more because it's a kind of a new theory. So for the TFA, we can measure distances from what the right thing, and also how hard the question was. So the TFA allows us to say how hard the hidden variables that I didn't give to the neural network is, how deep in it is hidden. And that will tell us how well our network does for different hidden variables.
Perfect. Hava, thank you again. It's a very, very, very amazing and interesting talk. And hope you can stay with us all this week, perhaps. You're very busy, but you're invited.
No, you have very different, very fascinating conference. Thank you so much.
Thank you.
Thank you very much, Hava.
Bye-bye.
Okay.
Yes.
So
thank you very much for your talk. Thank you, Gonzalo. Well, we are going to have a break now. Hava, you are kindly, as Gonzalo says, invited. I hope in the next summer school that we have every year here, we should have having you here in our region. But as you know, we decided to make it all virtual because of the pandemic situation. But maybe in next events, we can count on you here.
It will be fantastic. Never been in Chile.
It would be marvelous. Okay, so we will come in 15 minutes for the talk of Piero Bonizon. Thank you very much again, Hava, and see you in 15 minutes. Thank you.
Hi. Buenos días.
Hi, Piero.
¿Cómo está?
Hi. Everything is okay, I think, with the connection.
Absolutely, yeah. Podemos hablar en español también.
Okay.
So I'm going to start sharing my screen to make sure that it's visible.
And I'm going to introduce you.
Okay, and now I have to put the right. Oops. Oh, come on. No, no relaxed melodies.
Okay, Piero, I will use this time to introduce Piero Bonizon. It is my pleasure to introduce him. I've known him for a long time. He was a professor at RPI at the time when I was a graduate student, and he was a member of my PhD committee. So it's a real honor. Well, Piero Bonizon nowadays is independent consultant specialized in the use of analytics for in the industrial AI and the machine learning applications. He was a former chief scientist at GE Global Research. GE is a global General Electric, is a global company, has many, many different application areas and so on. And he made his career there and retired in 2014 after 34 years of service. Dr. Bonizon has been a pioneer in the field of analytics, machine learning, fuzzy logic, particularly fuzzy logic for me, AI, and soft computing applications. He's a life fellow of the IEEE and the fellow of the AAA-I and the IFSA. He received in 2012 the Fuzzy Systems Pioneer Award from the IEEE Computer Intelligence Society and the second Cajas Tour International Prize for Soft Computer from the European Center of Soft Computing. That's a European award. And the Meritorious Service Award from the IEEE Computer Intelligence Society because he has been very active in promoting computer intelligence. He also served as editor-in-chief of the International Journal of Approximate Reasoning for 13 years. He has co-edited 6 books and has over 150 publications in referred journals, book chapters, and reference procedures with more than 10,000 citations. And he received 74 patents, that means applied research, issued by the US Patent Office. So, Piero, you have the floor. Thank you.
Thank you very much, Claudio, and really appreciate your generous introduction. By the way, first, 2 announcements. One is I'm going to leave Plenary with with the copies of my slides, so you don't have to take frantic notes. And on top of that, of course, the talk will be recorded. And secondly, in this talk, I'm going to go breadth first, and the idea is to provoke ideas. On Friday, I'm going to give a tutorial, and in that tutorial, we're going to go take some deep dives in 2 or 3 topics that I'll mention during my talk. So in this presentation, I will not describe at length how we did things, more what we did, and the how will be left for Friday. Okay, so first of all, it's my honor to be here, and I want to thank you all for giving me the opportunity. Let's just pass the title because not everybody knows what PHM means, and I noticed that. And so also industrial AI. What the heck is industrial AI? Well, strange enough, when I went to Wikipedia, I found a recursive definition, which is the application of AI to industry. That didn't help too much. But we're going to try to look for alternative definitions and define the components of industrial AI. Then PHM stands for Prognostics and Health Management. So those are seem to indicate like a medical term. And indeed, we're borrowing those terms from medicine and applying it to machines rather than people. So we're talking about diagnostics and prognostics, but we're talking about the root cause of potential failures of machines. And in prognostics, we're talking about what is the remaining useful life of that machine before we have to intervene, right? We'll explain why companies like GE and other big companies that sell expensive products care about PHM and why and how they leverage AI for that, so how this is monetized. I'll go very quickly through the evolution of PHM in the cloud, mostly with cartoons, and spend some time on the conclusion, especially trying to see where are we going from here, okay? In particular, I want, before in the evolution of PHM analytics, I want to focus on leveraging model ensembles, which is when we're using analytics to make decisions, we need 2 things. We need a confidence in the conclusion that allows us to make a difference in the action, right? And so we need analysis which are actionable. And sometimes we also need to be able to explain those, the analysis, right? If interpretability is a must. And because people need to be convinced that what the machine is telling them is correct, right? So let's dive into the first part of the talk, which is industrial AI. I already mentioned that in Wikipedia says, refers to the application of AI to industry. Well, big deal. So I went to my alma mater, GE Research, And they have a little better definition, more of a functional definition, say, well, industrial assets and systems largely managed and operated by humans. And that is critical because we have machines that are becoming more and more intelligent, that can do computing at the edge, that can maintain models of themselves in the cloud. But then we need to communicate the state of a machine to the humans who are supposed to maintain these machines. And as we'll see later on, we humans seems to be the weakest link in this chain. I will talk in a moment about the industrial Internet of Things and the fact that we have billions of machines, literally connected, more connection than humans on the planet. And we'll talk about some of the technology in the next slide. So a couple of examples. One example is digital twins, which is basically merging the data that stays at the edge and is computing at the edge and describes the current state of this specific asset. And by asset, I'm talking about aircraft engines that are flying on wing, right? MRIs, which are working in hospitals, locomotives, and so on. And then we have to understand that this machine is not alone, but it's in the fleet of other machines. So there is a baseline of normality that we can draw from the thousand and thousand of the units in the installed base, and then specialize, use that as a global model, and then specialize for the specific model. That's what a digital twin in essence is about. And we're talking about diagnostics and prognostics and health management. Some of you might remember these 4 slides. I think it's important to understand that analytics alone is not enough to do a real world application. You need 4 pillars, right? One is the industrial Internet of Things, in which you have a lot of signal processing, usually at the edge. You have communication issues. Sensors are becoming cheaper and cheaper. And so there is a proliferation of sensors, which gives you the redundancy that sometimes is necessary to lower the uncertainty of your measurements. And cybersecurity is critical for any mission, critical use of assets, right? Mobility and people, because eventually through mobile platform, for instance, we want to let people know about the state of these machines. And these machines, meanwhile, are talking among themselves, besides talking to the human. And there are a lot of branches in resilient control technology that can make this machine more intelligent in reacting to situations when there is not enough time for someone to intervene from the outside. Through this communication, we're generating a huge amount of data. This is a more recent estimate that in 2025, every day, there will be an additional 463 exabytes, which is a lot. It's difficult to conceive, right? Created every day in the internet. Not all of them will be part of the industrial Internet of Things, but it's enough to understand that you need a technology stack to ingest this large volume of data that is coming in, and at a high speed, right? And with the variety of things. They refer to them as the 3 Vs. And we'll talk very briefly about that. We'll also talk about the fact that once you deal with data, usually data is not so good, it's dirty. And it takes a lot of cleanup before they can be used as features in your models. But most of this talk will be devoted to analytics, which could be data-driven or knowledge-driven. And even though we'll be spending most of the time on the data-driven analytics, I want to emphasize the fact that your physics-based models are embodying the know-how, the domain knowledge of so many engineers, right? So there are thousands of engineers in the thermodynamic models that are used to track the behavior of aircraft engines, for instance, right? You don't want to say, hey, I'm a data scientist. To hell with your model. I'm just going to slap a neural networks and I can do better than you. No, what you want to do is leverage that. So more often, and we'll be talking about this over and over in the talk, more often than not, you want to use, when you're doing a mapping, you're going from X to Y, right? But if you're using a physics-based model, you can go from X to Y hat, where Y hat is the expected output of your system when everything is working like a charm, right? And then you have a Y, which is coming from your data, and you want to look at the residual between Y hat and Y and explain that away with data-driven models. So in essence, you are focusing on a smaller region of the solution space, right, from Y hat to Y, and you're already leveraging what the engineers told you ought to be the ideal answer if everything else would have been according to the parameters of your physics-based model. It is also a great way to increase credibility and user acceptance when your users are the engineers who are supposed to maintain this. Anyhow, let's go to the business model. Why PHM? Companies like GE, I could also mention other like ABBs or other competitors of GE at that time when I was there, don't get a lot of profits or don't make margins by selling a large ticket item like an aircraft engine or an MRI. They want to increase their installed bases because once you have a user, that user will be sort of tied to the OEM in terms of maintenance, and maintenance is a revenue stream that is derived from these sales. So it's something called condition-based maintenance means that instead of the trivial example is instead of changing the oil in your car every 5,000 miles, right? You would like to know how those miles were driven, if it's on highway driving or a bumper to bumper in the city, and have some idea of the viscosity or if you have any debris in your engine, and act accordingly, basically having an expected remaining useful life of your oil and changes just before it's necessary, right? And that is a condition-based maintenance. What happened is that instead of having unplanned maintenance events when something breaks and you have to fix it, you're trying to predict when you need to have your maintenance, and the maintenance becomes a planned maintenance event. And because it's planned, you have a horizon over which you can optimize your supply chain management, you can optimize your repair shop levels, you can make sure that skill set and parts are available in the inventory of the location where the unit is going to, and so on. And so if you have a contractual service agreement, as GE had with most of their customers, in which they pay, the customer pays a fixed premium, and then the OEM is responsible for the maintenance, but also for the availability and performance of the asset, then you are satisfying those contracts at a lower cost. The premium is fixed, you reduce the cost, you increase your margins. So leveraging, so PHM evolution, which I'm going to show you in a moment, is using machine learning and AI and CI, is the technology that enables you to monetize these contracts, right? Or these contracts, actually, the tool through which you monetize the technology, what I should say. So that's a business model. So let's go, there is an obvious cascade in PHM. You do data acquisition remotely on every unit of the fleet. Because you have a fleet, you have a very robust model of behavior that should be deemed normal. And normal behavior that is not single. You can have multiple operating points at which you're operating this unit, and they're all normal, right? So in the state space, when you're moving away from a normal state and you're heading to another normal state, it's okay. It's a correct transient. If you're moving away from a normal state into some region where you only have very few points and you don't have any normal operating point, that's an anomaly. So you have to distinguish. Anomalies are not simply, I'm no longer where I was, yeah, because you may be in a transient mode. The transient might have been too abrupt. So a lot of the covariance matrix, a lot of the components of your covariance matrix have been disrupted, or you may have a bad sensor, or you actually may have an incipient failure, which is what this is trying to capture. And in that case, you want to do diagnostics, which is the root cause isolation, right? Once you have the time of the real anomaly and you have ruled out false positives and you have a root cause, you say, well, based on the past, I should have this much life left. So prediction of remaining useful life is difficult for a variety of reasons, because one, what prediction of the future is always more difficult than explaining the past. But secondly, your models are dealing with data which was truncated, was censored with a C on the right, statistically speaking. And because you did not allow your units in the past to die, right? You don't have run to failure data. You intervene and you interrupt the decay of the remaining useful life. So predicting when you're going to reach remaining useful life is also has an extrapolation error from your data. And furthermore, you're making assumptions of the load in the future being the same as the load in the past. Of course, by controlling the load in the future, you can also stretch this remaining useful life to make it fit your availability for repair. Once that is done, the rest is, as they say in Spanish, pan comido, is simple, meaning that if your remaining useful life is measured in minutes, well, you don't have time to optimize anything. Safety is paramount, and you have the onboard controllers to take care and put you into limp mode, right, until you land or until you can safely shut down. If your remaining useful life is measuring days or weeks or months, now that becomes the horizon over which you're optimizing. Like I said, supply chain management, repair loads of your shops, and so on. Finally, after you've done all this, you want to collect data. How did I do it? Did I diagnose the correct cause? Was that a real anomaly? How was my prognostics when you removed the parts? Could you tell me the state of wear of those parts, right? And that's how you're gonna update your models and maintain your models instead of maintaining your assets. And we'll see how that is extremely crucial for putting a model in production. These two red stars are basically, or explosion if you prefer, saying out of all these, the two difficult parts are anomaly detection and prognostics. The rest is reasonably under control. With anomaly detection, because if you are cascading false anomaly detection flags, you're exercising this waterfall for no reason, and that's expensive also in terms of credibility, right? You cannot cry wolf too often, and then people stop listening to you. And prognostic is because if I need to control the variance of the prediction, otherwise it's not actionable. Right? We'll give you examples in a moment. So let's quickly explore the waterfall. The remote data acquisition, we mentioned it, there are many factors that help us managing this, right? Here I mentioned the first three V's, volume, velocity, and variety. Some people have added two more for marketing, veracity and value. But this is, I hope you can see my cursor, the fact that data is dirty. And many times you need a federated database system because it's scattered over a variety of databases, sometimes without a common key, which creates issues. And more importantly, it's not clean. So you may have tags for a variable which are in percentages and other which are in absolute values, and you have to reconcile the two before you do any join. There is something called Berkeley Data Analysis Stack, or BADAS as they call it, called Sample Clean, that basically try to automate data scrubbing. Data scrubbing is always the most difficult upstream task in these projects, and it's always underestimated in terms of how much time it takes. This is, and of course, Hadoop on the commercial side. So this was a snapshot some time ago of the Berkeley Data Analytics Stack. And you can see down at the operating system doing resource virtualization. Spark was basically the way to maintain multiple threads and avoid the bottleneck of reduce in MapReduce. And then many of these applications on top of that, here you can see Sample Clean. MLib is a way of generating models on demand, right? Where you go in a declarative mode, just like an SQL statement, where say, this is what I want, and there'll be an optimizer behind for your query in SQL. There'll be an optimizer for your model generation in MLib. It'll give you models on demand with more and more complexity and so on. Which means, and this is going to be one of the topics in my talk, that models will become commoditized. That is, there is no longer job security in knowing how to build models. You can have models straight off of a library in Python, right, in Java and whatnot. And what is important is you know how to use them and how to combine them. And that's what I'll try to convey in my message. Anomaly detection is, like I said, difficult. I'm going to give you an example. The most important aspect is being able to reduce false positive. And unless, of course, the cost of false negatives is such that you want to attach different costs to them. Instead of using accuracy, you use the cost of misclassification, as it happens in some applications. I do have an example, which I've used in the past as well. This is simply to give you an idea of the diversity of data, even for something as simple as aircraft engine anomaly detection. We have data which are timestamped. Each of these dots, which you can barely see, it's an event, a discrete event that happened at that point in time. It was generated by the FADEC or by the centralized maintenance control computer on the craft. And this code means something in a data dictionary, right? So there may be some tools that you can use, including random forest, which I'll be using over and over in my talk, and will be one of the topics for my tutorial on Friday, that you can use for that. Or you may have time series, which is what engineers typically deal with, right? And there are some very old techniques like the Hotland T-square, which goes back to the mid-30s, 1930s, right? That basically take all the raw data, and after normalization, it gives you a score from the covariance matrix that shows when things become abnormal, and try to do some variable attribution. That's sort of the old school. In this new school, I'm going to show how we're using a tremendously high fidelity physics-based simulator of an engine. And we're basically entering an operational envelope that we're simulating flying at different speed, which I refer to as Mach, at different altitude. And based on the altitude, there will be some ambient temperature and so on. And so as I'm going through that, I have 3 autoencoders or auto-associative neural networks, which had been trained. The beauty of autoencoders is that it's unsupervised learning, right? So I'm going to show that in a moment in the next slide. So basically, the output tries to reconstruct the input, and you just measure the reconstructing error to know that you have trained the network. What is the advantage? The advantage is in the choke node or embedding, because you have really compressed all your information in those few nodes in the center layer. And that is sometimes used as inputs for other models, right? So you can take those 3 nodes in this example and make them input to a feed-forward neural network, for instance, that does some better thing. But you can, the beauty of this, you can encode it under normal circumstances, and then when something abnormal happens, you'll see that there is an error in the residuals. When you compare the input with the outputs, your residuals will not be 0. And so instead of just having one huge autoencoder in the entire state space, you'll say, well, this is a commercial flight, right? So I'm not doing fancy maneuvers like a military jet. You know, I have a takeoff with climbing in altitude. I have cruise, perhaps a different level. And then I have a descending and landing. And so I don't need to completely tessellate my state space with rules. Here I'm just talking about when I'm cruising, everything is high altitude. Ambient temperature is high. Well, it would be reversing the, it would be very colder, but you can always flip, do a mirror image of the abscissa. And the max speed is high because that's when you're fuel efficient. And so the first neural network should be used under these conditions. As we are descending, you're still high, but now you have a medium and medium value for your speed. You're decreasing your speed, right? And the ambient temperature is medium. You say you should be using the second one, and where altitude is medium and these are low, you should be using the third one. Clearly, there is a transition between this state and that state, which is a transition between going from the first to the second neural network and so on. And this transition, instead of being a model selection, is a model interpolation using a fuzzy supervisory. Very simple for those of you who have done fuzzy controller. This is usually a supervisory controller that decides the weight for the low-level controllers and then does a weighted aggregation. The same can be seen here for model selection, right? The other question is, how do I know that these are the correct membership functions? That is, that I interpreted correctly the meaning of high altitude, for instance, or high max speed. Well, offline, before I start this, I can do a fine tuning of this membership function. And that, so in this example, we're using one physics-based, one neural network, one fuzzy system, and one evolutionary algorithm, for the price of one, right? This is very simple. This is what having spent decades building engines allows you to do. You have very good simulator of dynamic system and sensors from the engine. And so here you're saying this, I want to fly the engine. And here saying this is the level of deterioration, usually using a Kalman filter to do this estimate of my compressor, low power turbines and high power turbine, and basically efficiency and flow. It's a plane for each of the three, right? So you have 6 variables. And here is what are the reading I should be reading from the sensors, right? So those would be used to tune the neural networks. And this is your neural network, right, or encoder. And basically, let me just show you this in a cleaner note. Autoencoder, by the way, is what George Hinton used at the very beginning when he was looking. It already exists prior to Hinton, but he started using adjacent layers, trying to do using them as reduced Boltzmann machines and trying to do the training of that, because it's not easy to train this autoencoder. Usually by injecting some noise, it's easier, and then refining the whole thing using backpropagation. And it's interesting, this code, the layers in between, can be seen as a nonlinear principal components. In fact, you could actually create principal components if you do linear activations, or if you're only using a single hidden layer with a sigmoid. It's one way of computing that, but it's also used in many other applications beside dimensionality reduction. For instance, in image processing, for compression and denoising, and in natural language processing, the word-to-vec. So it's a well understood architecture, is present in most libraries that you might want to use, and it was very useful here as well. This simply shows the 3 regions for your flight, right, and the 3 auto encoders training for those conditions. And this, if you remember from the mid-90s, something called ANFIS, A-N-F-I-S, Adaptive Neural Fuzzy Inference Systems. This is the architecture of ANFIS, right? You had the input and the membership functions. These were the intersection of the state variables for the various conditions, generating a degree of satisfaction of it in the state space. And then this was just a normalization of those weights. And here in ANFIS, we used to have a linear polynomial in the state. Instead, here we're putting the neural network, right? But we want to interpolate among, and then we get the fusion of the weighted output of each neural network. This is a figure of merit, which is simply a normalized residuals and root mean square of the normalized residuals. And the residual is basically reconstruction errors. I couldn't find the word. And so at this point in time, you can see these are the residuals, right, for this membership function. And I had a few glitches here and there and said, could I fix that? And so I looked at where the glitches were occurred in terms of the variables. And I said, well, I think if I were to manually move this to membership function, that is, make this high value a little bit sooner in air temperature and Mac, I could barely read this. Could I improve the situation? Yeah, I did. So at this point, as I used to tell my students, never try to automate things that you do not understand how to do it. And at least you should try to do once by hand on a small scale, and then you go and automate it. So I said, okay, now I can automate this. And I'm gonna take two adjacent membership function and just grab them by the intersection, because I want the intersection to remain at 0.5. That's the best value for interpolation from our fuzzy control experience. And I'm gonna take the basis of the intersection, that looks like the base of this triangle, as the length. And so given my term set, I only have 5 values of x1 and L1. This is my individual in the population, right? And then this is how I do it. I use a very simple version of a genetic algorithm, which is indicated here, right? So this is my individual, I decode it. I now have a set of membership function corresponding to that. I fly my engine through a simulator, right? And with this membership function, I use the already trained neural network to get the residuals, and I compute the minus the FOM. Basically, I want my FOM to become smaller, right, in absolute value. So I put a minus to make sure that it will be the correct fitness function, going from a large negative to a small negative. And with that, I assign the fitness, the usual. I do a probability of selection using some 2 type of mutation, leaving the elitist in the new membership function, new generation, and so on. And soon enough, I reached some tuning of the membership function that improved the figure of merit. So at this point, I put the raw data and I look at the residual. Residual should be around 0, right? Difficult with a naked eye to see, is this normal or abnormal? But here's the thing. We put a step function in the ZT49 that corresponds to the exhaust temperature sensor. And this was a jump of an order of magnitude of 10, right? From 0 to 10. And we saw that some of the other residuals were also disrupted. But clearly, this was different from when we went into the simulator and we start saying the compressor, the low pressure turbine, high pressure turbines are deteriorating and then moving it from a high value of flow and efficiency to a smaller and smaller value. And I can see that this decline, right, is very smooth. So these are the same residuals, right? But the signature of an incipient failure is so different from the signature of a sensor failure. And I could, of course, simulate different sensor failures with ramps instead of step points and whatnot. But the point is, I have a reliable way of distinguishing between these two and removing false positives, not to mention the fact that I can use the autoencoder as a virtual sensor. So if I have a sensor failure, instead of scheduling the aircraft for maintenance, I say from now on until we fix it, let's use the autoencoder as a correct output of this sensor. Long explanation, but I think it was, in my mind, a nice examples of how to use different techniques and different models. That, by the way, the 3 neural networks, the autoencoders, were not competing models, were complementary models, right? They were local models, and the fuzzy supervisory gave us a way of transitioning among that. As we'll see in both diagnostic and prognostic, we're going to now use competing models in the ensemble instead of complementary models. And This is what I'm trying to say. Again, diagnostics is supervised learning using classification. Usually we have some blueprint of what we build. So we have expected failure mode. And as this is the engineering know-how, you can start postulating possible failures that you try to then use as labels for your classifier. Of course, you could also have a none of the above failure or no failure whatsoever. And we will see in this example, we had 6 possible failures. So this is a 7-class classification because the 7th class would be no failure. And we have 12 parametric inputs. Notice that this is not a large number. And so we can do certain things that we could not do if we had hundreds and hundreds of inputs, which would be the case in the next example of prognostics. When we're doing a fusion, this is just more tutorial that probably needs to be, I'll go into more details next Friday. We're simply doing an aggregation of this is a parallel structure, right? We have each model generating a specific output for a query, and we're fusing them somehow. Could be just a mean or arithmetic mean, geometric mean, and so on, whatever. And then we take the argmax of that aggregation. When we're doing a local and dynamic fusion, we're saying we're not going to look at all the points in your history. We're just going to look at the query, which is the pointing in under that for which we want to have the output, an answer, and we're looking at the set of peers in that space. That's why I said in a low dimensional space, you can do that. If you have hundreds of dimensions, you cannot have any peers, right? Because of the curse of dimensionality. And so we'll be using a different technique, which I'll explain later on in diagnostic fusion, which is a cart tree. Basically, instead of looking at hundreds of variables, I'm going to look at the variable which have a high information content, which were the component of the classification analysis and regression tree or cart tree. And so I'm going to have a reduced space to carve out this hypercube in that reduced space instead of a general feature space. Having said that, we will be basically looking at the information from these neighbors in terms of the bias. Is there a bias, which is a mean error? And what is the maximum absolute error, the mean absolute error among the neighbors? And that tells us that when we're operating these models in this point, this is typically the behavior. So we're trying to characterize the behavior of each model and use that information in a local dynamic fusion. So simply put, these are my training records. This is this is ground truth. So this is the target. And the error is the difference between the prediction and the target. And I basically want to say in a set retrieval, right? Usually around 5% hedge in this hypercube. What are the parameters, as I mentioned, for bias and mean absolute error? And here what I'm doing is simply a bias compensation, right? I'm removing, this Q means this is a bias based on the neighbors, not on the entire data set. And in this case, I'm simply doing a mean rule of that compensated prediction, but I could have done also a weighted mean in which I would use the mean of the absolute error locally as well, as we'll see later on. So we have multiple classes. We don't have simply sensitivity and sensibility or recall and precision. We have a confusion matrix. If you're on the mean diagonal, you're correct. And under no fault, these corresponds to the true positive ratio and the false positive ratio, right? We did this in a five-fold cross-validation and used neural networks, support vector machines, and CART. And you can see the values for each of them. And then using the dynamic fusion, simply doing a bias compensation where the bias was computed locally, right? We were able to improve upon, obviously, the accuracy of each model, but also over other methods of doing fusion. there'll be more on Friday about this. I just want to touch upon the doing some time management as well. I want to make sure I have enough time to get over the end. But prognostics, after removing the false positive anomaly detection, prognostics with a small variance is the most difficult part of the whole cascade. And I already mentioned why that's difficult, because of the extrapolation that we are sort of forcing, which means that when we're doing prognostic, we should try to control the extrapolation. And I'll show you that in a moment, extrapolation error, by limiting what we're pushing in terms of control action. It is also the case that, as any good engineer knows, when a problem is difficult, sometimes reformulating the problem makes it much simpler to solve. So if instead of saying, I want to come up with the real value on the remaining useful life line, right, which is a single point with the variance around, that's the most difficult way. I could say, well, all I really care is take this remaining useful life and bin it with adjacent bins, and that's a partial ordering, right? That's what underwriters do with insurance products, right? They don't say, oh, this customer is gonna die in 3.5 years if this is a term life. It simply says, this is gonna be a high risk customers, right? Or if they say this is a low risk customer, they're using classification rules to place all the customers that are similar in the same bin, and they'll become indistinguishable in terms of an action, right? Or you might want to say, I want a complete ordering because I want to see what is the distance between first and second and third, and so on. Or you can have a cardinal, or I'm sorry, the complete ordering would be first, second, and third instead of being all indistinguishable in the bin. Cardinal ordering being I also have a distance between first, second, and so on. And that is if you have limited resources and you want to prioritize them for calibration, power management, and so on. Or, and this is actually used quite often, instead of saying, I want to know when this machine is going to die, you say, I want to know if there will be any end of life events in this time interval between T0 and T1, because that's when I'm going to operate it. Then after that, I can put it under maintenance and is no longer mission critical. And that corresponds, for instance, to term life with insurance, right? But also corresponds to the next example conveniently. So, so here we have 63 variables. 20 of them are time series, and 43 are those messages which are discrete events we mentioned earlier on. And we were asked to predict when a flight deck effect, which caused delays and cancellation and is reported with the FAA, would happen over the next 5 flights. This was Boeing asked us to do that a long time ago. 0 false alarm. We could not cry wolf even once. So in the ROC curve, we're just operating with attached to the y-axis, right? With the false positive equals 0. And we use random forest, which again, if those of you are not familiar with, will have to take my tutorial on Friday, which is basically a collection of cut trees. I'll give you a very short summary in a moment. And it has the advantage that it can use both inputs which are real valued or inputs which are discrete. And we're able to anticipate 86% of flight deck effects over a window of 5 flights, at which point the customer came back to us and said, well, probably I gave you a problem which was too easy. And they were right, meaning that if the measurements are recording the deterioration of performance 5 flights away from an event, right, the signature should be pretty obvious, pretty evident. And so they said, well, let's make it 100 flights instead of 500 of 5 flights. And that stretched the window, the horizon of a prediction, and made it very, very challenging. But again, the fact that we're using a collection of trees, right, was such that, like in this one, this tree would see something that would cause a false alarm, but the majority of the other trees did not go for that. And so the fusion did not create a false alarm. And when you have a large number of trees and the trees have been created with diversity, now I'm preempting myself, you are also shrinking the variance of the aggregation. And so you can have a fusion and then look at 2 or 3 sigma away from that fusion and make a safe action to say, it is time to intervene now, right? So you use the asset's life as much as possible within safety margins. So what is the magic is the fact that random forest is embarrassingly simple, meaning you only have 2 hyperparameters to define, right? How many trees in your forest, and usually 200 to 300 is good enough for most applications. It saturates after 300 in my experience, maybe 500 in very difficult situations, but again, it's very small return on investment. The models, which in this case are cut trees, are diverse by construction because we're using bootstrapping. Sometimes it's referring to as bagging, which bagging stands for bootstrapping in aggregation, which means that only 63% of unique records will be used in the training of each tree. So we're systematically creating a bias in each tree by depriving the tree from 37% of the data. And this is in terms of records. In terms of column, which will be your features, every time that a node in a tree has to be expanded into a subtree, instead of using all the n features, we are using m, and m is the second hyperparameter. But again, usually we have some heuristics for classification. Typically, square root of n is good enough. And m is also a very robust parameter. So with these 2 hyperparameters, which are basically given to you by default and they're very robust, you now have a very powerful technique, right? While a random forest only uses an arithmetic average, as we'll see in some other examples, a dynamic fusion, instead of basically using fusion as a meta model instead of just an analytic function, would further improve the outcome of the fusion. I'm going to skip the control aspect, and optimization simply means that, okay, now I'm making money, right? Up until now, as a company, I invested in the analysis. I want to optimize my supply chain management, minimize my cost, right? Maximize availability for the customer and performance, meaning efficiency. And so we have many, many techniques. I know there are some experts. Carlos is going to give a talk if he already hasn't, on multi-objective evolutionary algorithms. That's my favorite technique for this. I will show you a very simple example in which we use that in combination with neural network. Because if you can optimize the maintenance, you can also optimize the operation of the asset. So this is, and usually you can use simulators to evaluate the cost effectiveness. And you always have a trade-off between life, erosion, and meeting the load, right? So if it's summer and the price of spot electricity goes through the roof, right? You might say, hey, I'm going to squeeze more energy out of my turbines, right? Even though I'm eroding somewhat life because I'm running it. I'm sort of running on a semi-empty turbine life. But again, these are, once you have a Pareto of your non-dominated solution, you're basically using preferences to make a decision out of those. So this example, which again, I've used in the past, but I found it very useful. And again, I'll be using this example in my tutorial to see what we're doing with this neural network. Instead of one, we're going to have an ensemble of neural network. But for this talk, we're only going to have one. We have about 23 variables, control variables, that we need to regulate with a multivariable controller. So these are like your set point in your thermostat. There is only one. Here you have the excess oxygen, the angle of injection of a pulverized coal that is creating this rotating fireball and so on. What you want to see here, let me see if I have a better picture here. You have You want to minimize hit rate, which is a product of the inverse of two efficiencies. So meaning that if you are at a high temperature, you're more efficient, and that would be good because your hit rate is lower. But at a high temperature, you're also emitting more NOxes, right? And at past 0.6, you'll be fine by VPA. Less than 6, you'll be getting credits, NOx credits, that then you can sell in the open market. So what you really want to have is a Pareto function, and then based on the cost of fuel and the value of NOx credits, find the vector that is tangent to it to say this is the operating point I want to be at. But in reality, what you see in blue, this is where this machine had been operated, all inferior solutions, right? And so you're scratching your head and you say, okay, wait a bit. Here I'm using this set point as input to a neural network. The neural network has some constraint. It has to be equality constraint for the load because I need to be generating that load that I bid. And I have to stay below some threshold in CO and SO. And then these two neural networks will place me in a point in this space, right? So once I'm in this space, what you can see here is sort of an image of your training history. And the Pareto, sadly enough, there aren't any points on the Pareto. So whenever I'm trying to say you should be here, I'm extrapolating from my training set, which means I should really be very careful about how much about extrapolation error. It is also the case that if I tell the operator, you should be here and give him a control vector of set points, right? Which has never been used in the past. The guy who says, you're crazy. How do I know that this is not going to break the machine? So we, in order to handle both situations, we said is, okay, we would like to be here, but if this is the closest point we have been to, and this is the ideal point, let's move in this direction by just extrapolating 5% in control space. So that 5% will limit the extrapolation error, but also will allow a user acceptance. It's not too far away from something this guy had used in the past. So you deploy that set point, vector of set points. You record the value of NOx and heat rate for that point. You do this many times a day. And at night, you retrain the neural network. And now you have a few more points, blue points, a little bit closer to the Pareto. And you keep doing this day after day. So you're basically inching your image towards the Pareto, right? And this was simply to show that could we move the needle? Yeah, when we're in the middle of this curve, we had a 1.2 improvement in hit rate and 18% in NOx. If we were moving to minimize hit rate, we'll improve 2.5%, which is a huge amount of money, by the way. And when we're saying try to minimize NOx as much as possible, regardless of hit rate, the NOx improved by 27%. So that shows, yeah, that even at the extremes, you will not be breaking the machine. That was important for credibility. But also, we have now the capability of determining where the Pareto points are. And the difference, like I said, is with optimization, you want to sample your Pareto points as much as possible. You're limited by the population size unless you use an archive to increase the sampling of the Pareto. When you have to make a decision, you have to go from those hundreds of points down to one. And that's when preference comes into the picture. And finally, we will, the lessons learned from this one is that we need to update your models. Otherwise, the models become obsolete, right? And you ought to have the equivalent of a model PHN, right? To know if your models is behaving according to the stats of your testing of a model. And if not, so that would be the anomaly. If it doesn't, if the diagnostic would be which kind of model failures do I have? Am I operating outside of a training set? Or do I have a deterioration of my data and the model needs to be retrained in any case? If the model is used in an ensemble, I could do a corrective action, right? And say, I'm going to lower the weight or make the contribution of this model 0 in the aggregation. right? Assuming that I assume how much longer I can run with this model, right? And updating models is not that difficult, but when to do it is a critical aspect of this. This is simply before the cloud. That was me, the magician pulling out a rabbit from the hat. And this cartoon simply tries to evoke the scientific method where you have a theory, you design some experiments to see if you can validate the theory. Once you're happy that you couldn't find any counterexample, you try to axiomatize it and prove it. You then embody in some kind of tools, like this is backpropagation, and this is your MATLAB neural network toolbox. And so you just bought the license. It doesn't make you an expert, right, in neural networks. You still have to apply that toolbox to a problem. So when you're doing by hand, you're going through all these steps and you're running experiments until you find the right structure and the right parameters. And you have manually encoded this. And when something happens, you're the guy who had to fix it again, which means it's great job security, but it's not a sustainable process, right? So the first improvement was using meta-heuristics in the model space, such as evolutionary algorithms or other kind of meta-heuristics. So there is a much faster cycle running experiments with different models, and you are sort of, you promoted yourself to a higher level where you work more with editing the training set to make sure that you are maintaining the training that the training is up to date, as well as providing information about the cost of your misclassification, for instance, false positives, false negatives. And fusion typically is still static. And now with the cloud, we can do this in spade in the cloud. Right? We can do many times, so we can generate a huge amount of models, which is why I said that new model building is becoming commoditized. And we should be smart as to how to fuse these models using a meta model. And again, I'll be spending some time on Friday on this topic. There isn't too much time, and look, I'm seeing the clock, and it's been almost an hour that I talk. So I want to get to some suggested research areas and just focus a little bit on fusion and how to leverage domain knowledge or first principle models with your analytics, since most of us are engineers, we like that, and then conclude. So this is an eye chart. Again, you'll be given this slide, so you don't have to worry about it. But on the data-driven side, you have the 5 V's, which are shown here. And again, most of the times, vendors provide the solutions to that. Not forgetting that we're dealing with people, we are the weakest link, as I said, in this particular chain, because I always give this example, which is rather, what's the term, discouraging. In 5 years, all the machines that you're dealing with have at least double their capacity in terms of processing, storage, memory, CPU clock, bandwidth, and so on. 5 years from now, our cognitive capabilities at best are the same as now, right? So we are going in our derivatives have different sign, especially once you reach my age, and which means that it's very difficult for most of us, unless we are trained mathematicians, and I'm not, to visualize high-dimensional spaces and understand transitions of states in high-dimensional spaces. So there is a lot of effort in doing this. There are also temporal issues where streaming data analysis is so different from batch. There is I just want to show this slide, right? This is batch data analysis, right? Everything is there. You can put it in memory. You don't have any very strong time constraint, right, in terms of real time. This is real-time streaming data. This is like captioning a real life TV, right? Once the sentence is gone, if you haven't put a caption, you don't have any more opportunity to do it. And so there are very different techniques that you need to leverage. But back to this, I want to spend model life cycle could be a talk in its own right, and so are the topics like data learning in terms of convolution neural network, which is a great way, by the way, to get embeddings. But I want to spend some time in fusion, and the fact that the key word in fusion is diversity. Diversity, as I will, again, this is another commercial for my tutorial on Friday, is what happens when the correlation of the errors of the models in the ensemble is low. So if I want errors that make different type of errors, which are lowly correlated, it just doesn't happen by accident. It has to be injected in the design. And so it can be done by bootstrapping, right? Which is a parallel architecture, boosting, which is a sequential architecture, random feature subspace, which is the work by Hall in the early 90s, which Brayman then utilized in random forest, both records and features, which is, again, my commercial for random forest on Friday, stack generalization by Wolpert. And if you're using genetic programming, you can use different grammars, different function sets as a way of creating a structural diversity in the type of analytic models that you're being evolving. I want to sort of spend the last few minutes with agnostic fusion, which is, this simply says why physics-based and data-driven analytics are very complementary in nature. It's difficult to have a causal model with your data, while most of the first principle models embodies causal knowledge, right? And they're trusted by the customer. Sometimes our black boxes are not. But unfortunately, the physics-based assume some kind of a ideal state of the components, and it's very difficult to find the parameters that ought to be tweaked in the physics-based model when you know that some real component had been changed, right? That correspondence is not obvious. You can use Kalman filter for some of them, but not always. While it's very easy to retrain a data network, a data-driven network model to reflect changes, right? You just have a new behavior and you retrain the model, and so on. So being able to integrate the two is quite useful. We have seen this before, right? When we have a parallel architecture, and this was an example where we had a ball bearing in which we injected a fault by creating a small incision in the bearing, and then tried to use different type of models. This was a DARPA project many years ago, and in each of them would have some specific prediction of remaining useful life, but the solid line is a fusion of them, right? And then we took 3 sigma from the fusion to say now it is time to change it. So for safety, but we were able to squeeze to predict the life of this failure with enough time. This is a different example in which we have a very high fidelity physics-based model. Could be a computational fluid dynamics, for instance. And you know that it takes forever, even on a supercomputer, to run in different parts of a state space. That's the price you're paying for the high fidelity. You cannot run it in real time, right? But you can do a design of experiments to generate a large number of points in different parts of the state space and create a training set with which you are creating a fast approximation of this model, for instance, using a neural network. And then you're taking the real data, right? And you can have another training set that says, well, this assumes a certain level of deteriorations. This assumes the current data. And then when you have a real-time input, you're passing through the approximation to your physics-based model to get an expected output. And then you use a second one to correct it, okay? We did this, for instance, in the case of power generation, exactly in the same fashion, right? ARES was a great simulator of a turbine, but it was very slow, and we were able to approximate it with a neural network and then correct its output using the data. This is what I would like to end my talk just before the conclusion. I said that when we have a large dimensional space, we have a curse of dimensionality, meaning it's difficult to find a hypercube in, say, 200 dimensional space with any points in it, right? Unless we made the edge extremely large. With CART, on the other hand, I'm taking 200 features, and I'm only using the most informative one to create this CART. And so basically the height of a tree is the number of features that I have to, that I'm considering out of the 200 or so. And when I'm in a region, which is a leaf node in this CART, means I'm here in this hyper rectangle, and I'll have other points which are my peers. And those are the peers that will be attached to a query if the query falls in this region 4, right? And any kind of bias and local bias compensation and local weight will be used, will be actually attached, precompiled in this CART tree. So think of this: in database, you have indices to improve the performance of a database. Now you have a database of models, and each model has a CART tree, which is its index, right? If you want to know when to use a model, you just drop it into its CART tree, find the region, the leaf node, and get the statistics for that region for a model when a query falls in that region, right? And that is a great way for doing bias compensation and relevance weights for dynamic fusion. I want to show you an example in which we did this with models which we did not create. So this was toward the last year of my tenure at GE. We had something called FlightQuest. It was run by Kaggle, Kaggle.com, which is a site where data scientists compete for prizes, right? So we actually gave, I forgot if it was $100,000 or $125,000 to the first prize, all the way to the fifth place. And so at the end of the day, we were able to use 5 models from the vendors, from the competitors. And this is actually a slide from the winner organization that shows that there were about 26,000 domestic flights per day in the United States, and they used 87 days for training. And what they were trying to determine was the expected runway arrival, which is when will the plane land on the other airport, and then expected gate arrival, which is what it would take for the passenger to show up at the gate. So clearly the first prediction is based on weather and a flight path. The second prediction is based on ground operation at the airport, right? So typically the second prediction is an offset from the first one. First, once you arrive at the runway, what is the delta to get to the gate? And that's how most people formulated the problem. In terms of feature, they had 258 features that accounted for mostly from FlyStat, and they did a feature selection, reducing that to only 58 for the runway arrival time, with remaining what is this? 26 for ground operations for the gate, and use both generally boosted machine and random forest, right? They were able to predict with quite good accuracy both ERA and EGA. So what we did was, okay, we only had, unfortunately, 2 weeks for testing, not training, but testing. So I wanted to see how the model performed on, not on training data, but on test data. And we used the first 7 days to get these meta models, that is to understand what the CART tree of each of these 5 models would look like, and to have enough data to compute the local biases and the weight with which we will aggregate these models. And then in the remaining 7 days, from day 8 to day 14, we applied the fusion to these models. And sure enough, in 5 of the 7 days, the fusion was better than the best of each model. Of course, you don't know which is the best model until all the until ground truth is known, right? Until the passenger have arrived to the gate or the plane had landed on the runway. And in the other two cases, we were the second best. So that simply talks about robustness of fusion beside the accuracy. We talked about this already. I'll talk about what happens when you have a very large data set measured in terabytes, where even 63% is a lot, and is a lot of data to handle. And then we'll be talking about the bag of little bootstrap. We'll do this in this another commercial for my tutorial. So in conclusion, so we can wrap up this. In the past, we used to handcraft models. That's obviously no longer the case. Then the more recent past, we use meta-heuristics to explore model space and create an ensemble of models. Currently, we have to use a technology stack to ingest a large volume of data that are coming very fast. That's a big data issue. But again, Hadoop provides a very robust set of techniques for that. Diverse is the key number, right? If we want to use, and the combination, of course, of cloud and edge. But if you fell asleep during my talk, just remember the word diverse. That's what you want to have in your models for the fusion to be useful. There is a huge library of machine learning available for CNN. Convolution neural network, this is not a TV channel, has been at the forefront of using autoencoder. A lot of computer vision application, but a lot of them can also be used for the industrial application we mentioned, as well as long short-term memory, which are recurrent neural networks. And I believe that it's important to harness the commoditization of model automated model building, being able to do it in an agnostic fashion, such as the way we did in the competition with Kaggle, and put our efforts in meta models to make our fusion more intelligent, as well as automating model life cycle management. Because if you're an academician, you just develop a model, run your experiments, document it in the paper, and publish it. You're done with the model, right? You don't care if that model is still valid in a year from now. If you put the model in production and other people are counting on that model for the business, that model better be accurate a year from now, so you have to maintain it. And those are very important issues. And again, just like you should not be generating models manually, you should not be maintaining models manually, because big data also implies a big number of models. Anyhow, I took enough of your time, and want to thank you for your attention, your patience. And if you have any question, Claudia, you can. Thank you. Traffic.
Thank you, Dr. Bonizon, for this fantastic talk. And I have some questions that I will pose to you right now. The first question is, how can we get data if the failures in machines are the most important secret of an industry, of a company? The laboratory data in most cases are not representative of a problem in industrial machines.
You touch a real issue. Data is also, I'm trying to get to see your faces. There you are. Data is proprietary for most companies, and so they do not give the data away easily. They may give you, in some cases, I convinced GE to do it, a copula. Copula is sort of a compression, a statistical aggregation of your data without giving away the data, but it still maintains a lot of correlation information. But yeah, I don't have an easy answer for you. I'm sorry, Claudio. The best way is to find a mutually satisfactory agreement with a company. In fact, by the way, when GE sells an aircraft engine to an airline, right, the data belongs to the airline, not to GE. The only way GE can have access to the data is by saying, hey, if you're giving me a contractual service agreement and I'm responsible and GE is responsible for the maintenance, I need to have access to the data.
Yeah.
Right. But without that, it's data is wealth, is the new oil, right? That's the mantra, right? And so you have to convince that they have something to gain in giving you access to the data.
Does GE sell any engines without maintenance at all?
To my knowledge, only Lufthansa was trying to do their own maintenance. I'm not sure that they're still doing it, but no, everybody, you see, there is a warranty period during which, of course, the OEM is maintaining the engine, but the warranty period expires and the engine has a life which is at least another 19 years or plus, right? So, and it's a big investment, so there must be a plan for the maintenance. And typically, the OEM is the most suited agent for maintenance there. There is also, of course, data which are public data, publicly available data. In the case of a Kaggle competition, FlyStat had all the flight data information, right, weather and whatnot, all in one place. So for certain academic application, there are sources of public data, but for industrial application, you need to find a legal solution to that.
Yeah. This is a completely different question. This is from Pablo. Can you tell us about the IEEE to 2023 and efforts related to industry and NI?
Absolutely, a commercial, yes, Pablo. So IEEE CIS is very dear to my heart, as I was in the executive committee of the society when it was still a council of societies. So I came from an industrial background, even though I enjoy being an adjunct professor at RPI for many years. But I see that most of the industrial participation is not there. We have industrial members in CIS. We did some kind of survey, and about 30% of the responders to the survey were from industry. Yet there isn't a strong active participation of industry. So we decided that all our conferences are basically aimed or structured for academicians, where people submit papers, the papers are reviewed, they go into the proceedings. And excuse me, this is probably my son asking me why I'm not answering my phone. Oh, Stefano, I'm on a Zoom. Can I call you later? He calls me every day, which is nice. He lives about a mile away. And he's on the way dropping the grandkids. Back to CAI. So we decided to have something which was industry focused instead of academia focused, and have participants from the industry telling the audience what are the key challenges the industry has that ought to be addressed by AI and CI, instead of just individual solutions to problems that may or may not be the real ones. And so in 2023, about a year and a half from now, Gary Fogel and I will try to organize a conference on AI, which is being sponsored by 4 societies: CIS, Computer Society, Signal Processing, and System and Cybernetics, with the idea of creating this place where a lot of keynote speakers will be from industry, will also be a few visionary from academia. And we want to have grad students presenting their work in poster sessions where they can mingle with the industry people who probably would like to hire them. That is, we're using grad students as a currency to attract industry to our conferences, but also helping them finding a good job, because it's definitely a highly sought skill by industry. I'll have more information in the future as we are trying to shape the program, but it will take place for the first 2 years in the Santa Clara Valley, which is Silicon Valley, because so many companies using AI are already there. So it'll just be, they don't have to take a plane to get to the conference. And we also can get many more keynote speakers or plenary speakers or panelists locally, right? So minimizing the logistics. and it will take place in June of 2023, the first week of June.
Very interesting. Thank you. I have
Welcome.
some more questions to
Absolutely.
share
Go
with
ahead.
you. Yeah. Could you make some comments about the diversity strategies for deep learning models?
Diversity, like I said, is usually injected with the training set. Okay, it is not specific to deep learning. I mean, deep learning simply consumes a larger volume of data for training, but it has to be a systematic removal of information, if I can define it that way, right? Whether it's by records or by columns in the data. If you think of the data being a data matrix, right? You have rows which are records, usually timestamp in the, if it's a, or not, and columns which are features. So random forest is perhaps one of the best, even though it's an old model, it's perhaps one of the best way of describing how diversity is created. I mentioned a few more techniques. Using different technologies is a way of injecting diversity, and that's stack generalization, for instance. And that's what happened when we, in the competition, right? In the competition, we used models from the top 5 participants, regardless of which techniques they used. And it was an agnostic fusion because I was not looking at their code, even though we had it. I was not trying to make sense of their code. I was just looking at the behavior of a model and try to characterize the behavior of a model as metadata, capturing this card tree, and then use that information in the fusion, doing sort of meta fusion. So I don't have any specific structures and parameters, right, of the model. The parameters would be driven by the data training, but so will the structure. In the structure, you can experiment in an autoencoder. How many layers do you want to have in this butterfly-like, right? Again, in deep learning, you can. We have solved now the issue of training, right? We have not solved the issue of how many layers do you want in deep learning. Most of the time, this is experience from my son, who is using a lot of a Python library for a convolution neural network with embedding. A real advantage is in using the autoencoder in an unsupervised fashion, because all you're doing is minimizing reconstruction error, right? And once you have a very good middle layer, which is your embedding, use that as the input to a reduced model, which is completely separate from the autoencoder. The autoencoder is just to take data, right, and compress it into this middle layer, the embedding vector. And then the embedding vector is your refined information vector, which contains the feature for your other models. In his case, he's looking at proteins. He's a bioinformatic guy, and was looking at the sequencing as well as the the amino acid sequence of the proteins obtained by analyzing mass spectrographer, and looking at the physical chemical properties of those amino acids, and try to find a space in the embedding that contain where, if you cluster, you could find different sequence of amino acid with the same properties, with similar properties, as a way of postulating possible candidates for antigens and the like. Yeah. I'm sort of going off a tangent a little bit, but deep learning is too broad to, so I'm just using this.
For example, you talked about using 33% of the data.
Yes.
For the rest, why 63?
I conveniently have this slide here.
Okay.
Basically, what happens, just remove this, is that you have a Bernoulli series, right?
Okay.
And you approximate for a large number of n, this can be easily approximated as a Poisson. And so this is what you end up with. And for k equal n, right, this is the expression, and that's how you get 63 units.
Okay.
Okay, so it's actually a reasonable Poisson approximation. So every time that you're using sampling with replacement, right, and you want to have as many records as the original record from which you have been sampled, you're on average using 63% unique records.
The last question I have is, do you think that ensemble techniques are also useful when you have low number of training points, hundreds of points, and maybe generating synthetic additional points, injecting random noise in the training points, I mean, to enlarge the number of points?
If you don't have a large number of, remember, it's all about diversity, and diversity means you reduce the information when you're creating models. If you don't have a large number of points, I see it very difficult to do it. Yeah. I mean, there are, what you have to do is then limit the degrees of freedom, in essence, right? So
there's not much you can do.
Not much you can do. I mean, with random forest, what you could, typically do not prune any cut tree. You could put a ceiling to the cut tree to make sure that the cut tree doesn't go too deep, as a way of limiting complexity, but I don't know about how well it will perform. If you could expand, I'm sorry, for another way of expanding data is by using simulations. So simulation, if you can replicate the conditions of the asset that you're trying to simulate in terms of deterioration or not, right? Then design of experiments of using the simulator will augment your data. But you may be mixing things because the assumption may be different between the simulator and the real asset from which you're collecting real data. So sorry, I painted myself as a magician in the cartoon, but I'm not a magician.
Yeah. You at the beginning of the talk, you said something about cybersecurity. Can you comment a little bit about that? Because that's really a problem, especially if we are all going to be connected in the cloud.
Yeah, my advisor used to say an expert is someone who can afford to say, I don't know, but I don't know about it. Cybersecurity is such a different issue. I mean, there are all sorts of issues within cybersecurity, of course, and some of them, like intrusion detection, right, can be handled with some of the anomaly detection techniques, because there's almost a one-to-one correspondence between the function that I mentioned for PHM and the same function for other type of application, financial and commercial application. So fraud detection or intrusion detection are the same as anomaly detection. It's basically an aberrant behavior or abnormal behavior. So once you have a baseline for normality, any deviation from that is an anomaly. And so part of that would be cybersecurity. But cybersecurity has so many issues that, in fact, the Internet of Things, right, the IoT, to put another I, make it industrial Internet of Things, cybersecurity is critical. I can only give you some example because I don't have the answer to your question, but there was a case of a casino in Las Vegas that was hacked through the temperature sensor of the water in an aquarium. So there was a huge aquarium that was, as a decoration for the players, and somehow it was part of the IoT. They hacked into that. They were able to go into the database and harvest credit data of high rollers. So that's just an example. And this is sort of a trivial example if you're not being hacked with your credit cards, but it's a different ballpark. I simply consider that a requirement, but I don't have a solution to that.
Yes.
AI
Okay.
does have some possible solution. I just have not worked on that.
Okay, we want to thank Dr. Bonizon. Now it's 1 o'clock and probably a lot of people want to have lunch. And it was a great pleasure, and we will see you again towards the end of the week. Thank you again.
Thank you, Claudio. Thank you, Pablo. Thank you, everybody, everybody else. Ciao.
Ciao.
Thank you. Thank you very much, Piero. Thank you for your interesting talk. I want to give some instructions for the afternoon, where you are, of course, Piero, invited. But first of all, I want to say that the technical sessions in the afternoon start at 14:30 to 2:30 p.m. And there will be in parallel 2 sessions. In room A, you will have 5 presentations. Now it is for tracks ESA-ESC and and in the room B, it will be other 5 presentations. So it starts at 2:30 and ends at 4:10. Okay. You will be able to reach the sessions through the platform, the Syntec platform. I will go there to show you. Excuse me, here. You will see the 2 sessions of room A and the 2 sessions of room 2 that are in different times. Okay. Please remind that it's 2:30, not 3:30. Okay, I'm not sure why the platforms makes a mistake here, but go to the original schedule. Okay.
Since we have, since we have different time zones, different people are watching probably, it's 1.5 hours from now, right?
Yes, it's 4:30 in Chilean time, of course. Thank you, Claudia. Yes, 1.5 time break for lunch. So thank you very much to all the key speakers that are here and all the participants, and we see you in the afternoon. Thank you.